Welcome to our OpenPOWER Academia and Research AI and HPC workshop, part of the CINECA's team. And thanks for joining today for the workshop. And thank you for the CINECA team as well as the key organizer from CINECA side, Dr. Massimiliano, for his support, wonderful support for the last few weeks, to make this happen. And also welcome all the participants, from worldwide, for this workshop. And my pleasure to have you all here. And we have key presenters, along with, Dr. Massimiliano from CINECA, Italy. And the other presenters are, I just want to name them now. Dr. Jose Morero from IBM Research, Dr. Samir Shende from University of Oregon, Dr. Panda from Ohio State University, and Brian Allison from IBM Systems, and Florin Manila from IBM Europe. Welcome you all for this, today's, the workshop at CINECA. And we have our special guest, as a panelist, Dr. Agya Das from University of Wisconsin. Thanks for your support always, as a panelist and also a key presenter too, in most of our, previous webinars. Today's session will be recorded and shared. Question and answers will be end of every presentation for 5 minutes. And then you can raise your hands and as well as you can post questions in the chat window. Dr. Massimiliano, who is a scientist at CINECA, will be sharing the latest supercomputer experiences and, the Power 9 systems, what they installed recently. Please go ahead and start your presentation, Dr. Massimiliano.
Thank you, Allison. And now I'm trying to share the screen. I hope that, do you see my screen?
Yes, perfect.
Okay. Okay, thank you to all people that was involved in this presentation and this workshop, and thank you to the attenders to be here, even if remotely. This workshop was hosted by CINECA, that is the main HPC center in Italy and one of the most important in Europe. Currently, CINECA is an inter-university consortium that merge together the most important university of Italy. It gives support and resources to university, scientific institution, but also to the Ministry of University and Education, and give also service to private communities for industrial development. The main focus of CINECA is to promote the use of HPC resources to increase the capacity of European researchers to do good science. To do this, his focus is on innovation and technology transfer, and currently we start to develop new line of research in big data and machine learning, artificial intelligence, and so on. So regarding the capacity of do HPC of CINECA, this is the position of HPC cluster of CINECA in the top 500 supercomputer list during the last year. As you can see, on 2012 we was on position 12 on the list, and a few years ago with our old tier 0 machine we was in position 12, and currently during the last month I think a couple of months ago, we also deployed a new machine, one Marconi 100, that was ranked on the same list and at position 9. This is the second time that an Italian machine was ranked on the top 10 of this list. And currently, another important thing to say is that Italy is the only one country in Europe that was in this list. And Italy was also the only one country in Europe to have 2 machines on the list, and also the only one machine that was deployed by a private enterprise. Okay, this is the structure of our HPC facility. Currently, we have 2 tier 0 machines, the old one Marconi that was equipped with more than 2000 Skylake nodes, and the new one that is Marconi 100 that we will see better in the following slide is an OpenPOWER machine. And all these machines are connected throughout 100 gigabyte Ethernet network, and this network connects the 2 tier 0 machine with our tier 1 machine Galileo, that was a smaller machine, only 1000 nodes with 2 Broadwell processor per node, and a new machine that was developed for cloud services, Meucci. As I told you before, all these machines are connected throughout 100 gigabyte Ethernet network, and all the machines are connected to a disk facility named DRS and to a tape library. Currently, our top machine is the Marconi 100 system, that is an IBM POWER system with 980 nodes. Each node is equipped with 2 IBM Power 9 processor, 2000 gigabyte of RAM, and 4 NVIDIA V100 GPUs. To give you also some other number, the total number of core of the machine are about 350,000 cores, and we have about 250,000 gigabyte of RAM with about 4,000 GPUs. The network that connects all the nodes of the machine is a dual-rail Mellanox CDR InfiniBand network, and on the top 500 of June of this year was registered a LIMPAC performance of 21 petaflop of computational power sustained. As theoretical peak performance, the machine have about 30 petaflop of peak performance. And this is I think, the most powerful public machine in Europe. If you want to have access to our machine, you have various possibilities. The first one, if you are an European researcher, you can apply at the European level throughout price call. You have the possibility to apply both for large project as an order of magnitude from 100 to 1,000, 100,000 to 1 million of $, or you have also the possibility to apply for a smaller project, simply to develop your code, to port your code on our machine throughout preparatory access call, The only requirement of this call is that you are based on European institution, and clearly that you have to share the results of your research throughout the usual channels, for example, article or paper or presentation, so on. Another possibility that you have is if you are an Italian researcher, you can apply at national level, and for mid-size and small-size projects, for example, from 100 to 1,000 to 50,000 node hour, and in this case you have more call per year, and it is also easy to apply, and at the end you have also a third possibility, that is to do an agreement with CINECA, pay for the resource you want, and have the access to our machine. In any case, you have several methods to test our machine. In any case, you can also contact our user support to request more information, or see the link that I put on this presentation, that give you the possibility to register to PRAISE or to ISCRA in order to apply for this service. And for what concerns this presentation, this workshop, I want to say thank you again to Ganesan, and I'm sure that the presentation you will see today will be useful both for you, but also for us from CINECA. And I give the floor to Ganesan again to give you an overview of the presentation we will see today. Thank you.
Thank you, Dr. Massimiliano. It's I'm very glad to hear that, your supercomputer is one of the top, 10 supercomputers, and also, you are also granting access to many users, in Europe, and that's very important, for all of the researchers, who can get engaged on this, supercomputer and build new applications, to help out the world, for social cause and other stuff. Thank you again for the wonderful, information about the supercomputer, and also the things, which you shared. And any questions, audience, for Dr. Massimiliano before we go to the next presentation? Participants, as well as the panelists and the other presenters too, as part of the call. Any questions?
Hi, Dr. Gurasi. This is Arghya Das from UW Platteville. Can you hear me?
Yes.
Okay. So I have one question. So you talked about getting access for European PIs and everything. So is there any opportunity to get access for international users?
The PI needs to be European currently.
So I have to collaborate with some European PI and
yes, currently, yes.
I got it. Thank you.
Thanks, Professor Arghya.
One question. So do you have anything like the educational access, like for small amount of access? I mean, which we can share, which you can share with the students or something?
During the courses, yes, you can apply for a course from any places in the world, and you can receive a very small amount of resources to test your code.
Perfect. Thank you.
You're welcome.
Thank you, Professor Arghya, and thanks, Dr. Massimiliano, once again, for your support, as well as organizing this workshop at CINECA. And I'd like to invite our next presenter, Jose Morero from IBM Research, who is going to be sharing, the power innovations, the Power 9 and, the future things, as part of power, and this is going to be a very interesting talk. I welcome Jose to share the screen and, go ahead with the presentation.
Thank you, Ganeshan, for introduction. Thank Dr. Massimiliano for inviting me. Before I can start, looks like Dr. Massimiliano has to stop sharing his screen before I can share mine. Okay, let's try again. All right. Can people see my screen?
Yes. Looks good.
And it looks good. Okay, thanks, Ganeshan. Thanks everybody for attending. I will cover what I can in 25 minutes. I have probably more material than I can cover, but I'll focus on one aspect of my talk, which are innovations for high performance computing. And as people here in CINECA are well familiar, since the dawn of supercomputing, high performance computing has been about three things: number crunching, memory bandwidth, and interconnect. And we are now designing our IBM servers around a variety of computing technologies that we have made openly available to the community through the OpenPOWER initiative, including those three things: the number crunching, the memory bandwidth, and the interconnect. So I'll cover those three areas. I'll start with the actual processing, the number crunching part, then go on to memory bandwidth, and then go to the interconnect. And I will, like I said, I'll cover as much of it as possible. Is that okay, Ganeshan? Can I move on?
Yes, go ahead,
Okay.
please. Go ahead.
Okay, so IBM Power systems are built around the Power ISA, the Power Instruction Set Architecture, which has been evolving for over 30 years, since the times of the first Power processor, which people refer to Power 1, but it was called just Power, 1990, followed by Power 2, which was the first processor that I used when I joined IBM in 95. Including embedded processors used in the Blue Gene supercomputer, to the current Power 9, which implements the Power ISA 3.0, and our future Power 10 processor, which will implement the Power ISA 3.1. The Power ISA 3.1 is publicly available. You can see, we added quite a bit of new instructions, including prefix instructions and matrix math assist instructions that I'm going to talk about. We currently have about 1,400 instructions in our ISA, which seems like a lot. As part of the OpenPOWER initiative, there are subsets that can be implemented. A processor does not have to implement all 1,400 to be declared OpenPOWER compliant, but Power 10 will implement all of them. It's a full implementation of the Power ISA 3.1, including a number of new features that we put exactly to enhance the processing capability of our processor. The ones that are probably of most interest to people here are new 32-byte storage access operations, so we can load and store 32-byte vectors. We do that as loading and storing a pair of our vector registers. Our vector registers continue to be 128-bit or 16 bytes, so a pair is 32 bytes. We can load and store a pair with just one instruction. We have a new set of SIMD permute class operations, bit manipulations, mask manipulations, and a variety of translation management, copy and paste, which allows you to move large blocks of memory, persistent storage, and probably what would be of interest to the people here, and which I will go into more detail, matrix math operations. So the matrix math operations are designed exactly to accelerate matrix math. Before I go into those, let me talk about something that we did very significant, not only for for the immediate future on Power ISA 3.1, but for the long-term future of the Power ISA, with the introduction of the prefix support, which allow us to have what's essentially 8-byte instructions. All the instructions in Power ISA up to 3.0 were 4-byte instructions. Now we have 8-byte instructions, which means a significant increase in the address in the space of possible instruction encodings. So in the prefix architecture, we continue to have all the existing 4-byte instructions, but we can also now have a prefix, another 4-byte prefix with a primary opcode that was not supported in the old instructions. So anything that begins with the primary opcode 1 is a prefix, and that is 32 bits of prefix, which can either modify an existing instruction, the suffix, or can be a complete new, or can indicate that it's a completely new instruction, a completely new 64-bit instruction. So as you can see, this greatly enhances the capabilities of our ISA, right? We were really running out of encoding space in the 32 bits that we had, but now we have increased that space by 4 billion times by going to a 64-bit encoding. It's not honestly 4 billion, because the primary opcode of the prefix is always 1. That takes 6 bits, but you can do the math. And the main thing that we are adding in Power ISA 3.1 that can be of interest is PC relative addressing. So we can now loads and stores against the current value of the program counter, and MMA lane masking. So this is a form of the matrix math assist instructions that I'm going to cover next, and a lot of modifications for loads and stores that are very, very useful. So let me move on to the matrix multiply assist instructions. These are the MMA instructions which have been introduced in ISA 3.1. And they were designed to not only to lead to very efficient implementation of the instruction, but also to lead to very high performance in key computations in the space of technical computing, machine learning, deep learning, and business analytics. So the instructions that you see are, as you will see, are a natural match for implementing dense numerical linear algebra computations. And we also have shown applications to other related computations such as convolution. And I don't mean doing convolution through matrix multiply, which can be done with various forms, but direct convolution can also be done very efficiently using these new matrix multiply assist instructions, or matrix math assist instructions, as they probably should have been called. There's work going on in research, both inside and outside IBM, on how to do other computations of interest, like arbitrary precision arithmetic, discrete Fourier transform, using these matrix math assist instructions. So let's see what the instructions look like. Before we go there, just a refresher of what the vector registers in Power ISA look like. We have 64 registers of 128 bits. This has been around since Power 7, so about 10 years of these vector registers, which gives a lot of register space. And we are adding a new set of registers called the accumulators. And the accumulators are 4x4 arrays of 32-bit elements. We will talk about what happens with 64-bit elements later, but for the current discussion, let's talk about them as being arrays of 32-bit elements. So an accumulator is a 4x4 array of 32-bit elements. And the elements can either be 32-bit integers or 32-bit floating point. And from a software perspective, they look like shadows of 4 consecutive VSRs, but they must be managed in software mode. Data must be transferred from the vector registers to the accumulators, and from the accumulators to the vector registers. And that correspondence is fixed, right? So vector registers 0, 1, 2, 3 correspond to accumulator 0. Vector registers 4, 5, 6, 7 corresponds to accumulator 1 all the way up to accumulator 7. So the first 32-bit vector registers here, vector registers 0 through 31, are associated with 8 accumulators. And what does the operation actually do? Well, the operations do the equivalent of a BLAS rank K update of the accumulator with the vector registers. So let me go to the drawing here that may be a little bit easier. So if I have a 4x4 accumulator there, let's take the case of the 32-bit input elements first. I have a 4x4 accumulator in red, and I have two input registers in blue. They are 128 bits, so they have four 32-bit elements each. So one is treated as a column, the other is treated as a row. I do the outer product, meaning the all-to-all, right? I have four elements in a column and four elements in a row. So I have 16 operations total, and with each one of those operations, I update an element of the accumulator. And the plus and minus just show the four combinations that I can do, which is I add the accumulator, I subtract the accumulator, I add the outer product, I subtract the outer product. There's also a fifth combination, which is I ignore the accumulator and just do the outer product and store in the accumulator. So what was there gets destroyed. The old value of the accumulator gets destroyed. So there's 5 different variations for each one, plus 5 if you ignore the initial value of the accumulator. So you're not accumulator, just storing the result. And then there are masked versions where you can control which elements of the row and which elements of the column get actually used to update the accumulator. And then you also have a control of mask along the depth being the inner dimension here. So any questions about how it works with 32-bit inputs before I move on to the other size of input elements? No? Okay. So let's move on to the 16-bit inputs. If I have a 16-bit input, then my vector registers being 128 bits, I can have 8 elements per vector register. So I treat those elements as those vector registers are being 4x2 arrays. So if I have a 16-bit input elements, I do a rank 2 update where I multiply a 4x2 matrix by a 2x4 matrix, which produces a 4x4 result, and that updates the accumulator, which is always 4x4, right? In all these cases, the accumulator is a 4x4 array of 32 bits in elements. The input vectors may be different. The input vectors can be 32-bit elements, 16-bit elements, 8-bit elements, or 4-bit elements. So there's what you'll see here on the bottom of page 9 here is the different forms of the instructions here. With the first one is for 32-bit floating point. Then we have 16-bit floating point, 16-bit integer, 8-bit integer, 4-bit integer, and the size of the accumulator, which is always 4x4. The shape of the X and the Y inputs, which can be 4x1, 4x2, 4x4, or 4x8 arrays, and the number of multiply adds that each instruction produces. And in the case of a 32-bit input, you do 16 multiply adds because it's 4 input on the column, 4 input on the row, and you do 16 multiply add operations. But that grows as I reduce the size of the element to 32, 64, and up to 128 multiply adds on a single instruction. So for example, back here to page 10, if you have 8-bit input elements, each vector register input is actually a full 4x4 matrix. Now 4x4 matrix is 16 elements times 8-bit is 128. So using 2 input vector elements, I do a full 4x4 matrix multiply, and I update the accumulator. Again, the inputs are 8 bits, the output, the result is always 32-bit elements. Any questions? Okay, so if we move to 64 bits, it's a little bit challenging because the size of my accumulator is the same. So instead of having a 4x4 array, I have a 4x2 array of 64-bit floating point elements. The size of the accumulator in bits is the same. It's 512-bit accumulator. So I can either do a 4x4 array of 32 bits or a 4x2 array of 64 bits. So now I still want to do an outer product to update that accumulator, but I need a column of 4 elements and a row of 2 elements. So the way I get a column is by using a pair of vector registers. So I use X1 and X2 vector registers. Each one has two 64-bit elements. So the pair has 64 bits for four 64-bit elements. Y has two 64-bit elements. And I do a outer product or a 4-element column, but by a 2-element row. And I update my accumulator, which is 4x2. So in this case, I do 8 double precision multiply adds per instruction. Okay. So again, very high computational density per instruction, 8 double precision multiply adds, but more significant, a lot of computation per input data, right? I only need to read 328-bit registers, 384 bits total, to do 8 double precision multiply adds. So I read 6 elements and I do 8 operations, so very high density. Which is why our load pressure is very low, and more. I can even improve our load pressure by using multiple accumulators, right? So the instructions themselves always operate on a single accumulator, but I have 8 architected accumulators total, so I can create as a software construct these what I call virtual accumulators by tiling multiple hardware accumulators. So for example, by tiling all 8 hardware accumulators, I can build which are 4x4. I can build an 8x16 virtual accumulator. So now to update each one of those 8x16 virtual accumulators, I need to load 2 X registers, X0 and X1. I need to load 4 Y registers, Y0, Y1, Y2, Y3. So I need to do 6 vector loads, but I can do 8 instructions. So I only need to do 0.75 loads per outer product instruction. And I also have a way to tolerate latency, because since I have 8 accumulators, takes me 8 instructions to go back to the same hardware accumulator. So the latency within an accumulator it can be tolerated. I'm going to give an example next of what the code would look like. For simplicity, I'm going to use the 4 accumulator configuration. So it's an 8x8 configuration. So I use the ACC0, ACC1, ACC2, ACC3 hardware accumulators, each one 4x4 to form an 8x8 software accumulator. To do each outer product, I need to load 2 X's and 2 Y's. I'm going to load these using the new 32 byte load instruction. So this is going to be one instruction to load X0 and X1, another instruction to load Y0 and Y1, and 4 outer product operations to update the 8x8 accumulator. So I'm going to do that in a code to do the kernel of a matrix multiply, of a gem to be more precise. In the innermost kernel, what I'm doing is updating a small panel of matrix C, M by N, which in my case will be 8x8, by multiplying an M by K by a K by N panels of matrices A and B. Again, M and N will be 8. K in my case will be 96, could be anything you want. And I'm going to load a column of A, a row of B, outer product, the next column of A, the next row of B, outer product, all the way to the last column of A, last row of B, outer product, and each one of these outer products will update the accumulator. Okay, and the code is very simple. I'm not showing the whole code here. There's dot, dot, dot. I'm skipping steps 3 through 95 because they look exactly the same. But first thing I do, I have to load the accumulators, which the way I load accumulators is by loading the vector registers and then transferring to the accumulator. So I load 16 vector registers. I transfer them 4 at a time to their corresponding accumulator. And then I repeat 96 times. I load a pair of vector registers, which will be the X's. I load another pair of vector registers, which will be the Y's, okay? And then I do 4 of the outer product instructions, 1, 2, 3, 4, okay? So the 6 instruction kernel, the 6 instruction step, because this is inside the kernel, will have done an 8x8 outer product and an updated an 8x8 accumulator. And I repeat that 96 times, and I have done my kernel of the matrix multiply. I transfer from the accumulator to the vector registers, and I store them. Okay. And that's it for the kernel. The rest of the code is code that is already out there, for example, in OpenBLAS. In fact, if you look at the latest release, the latest repository of OpenBLAS, we have uploaded our code for that. I have to be honest, I don't know if it has been accepted already, but you can look at the GitHub and you'll see our submission there. So that's it in terms of the matrix math assist instructions. I'm going to proceed very briefly to talk about the improvements to memory and the improvements to interconnect. Any questions on this step here? Okay. So let me talk a little bit about the improvements to memory. So for a while, for a couple of generations now, we have been building systems that use either a buffered memory approach, where the processor talks to a buffer chip and the buffer chips talk to the memory, or more recent in Power 9, we have done systems where the processor talks directly to memory, which has advantages in latency also, but you do pay a penalty in capacity and bandwidth, right? So the non-buffered approach, the direct attached memory approach has lower latency, but lower capacity and lower bandwidth. The buffered memory approach has higher latency, but higher bandwidth and higher capacity. We're converging this in our next generation with a new standard called Open Memory Interface, where the processor does talk to the memory using a high-speed interface, and then that is a buffered memory, but it's a standard, it's an industry standard buffer chip that follows the standard of the Open Memory Interface. In fact, it's not produced by us, by IBM. And we have adds very little latency, but we still keep all the high bandwidth and the high capacity. So to give an idea, while the existing approaches are you can choose either a bandwidth of 150 gigabytes per second and a capacity of maybe 2 terabytes per processor. With the new Open Memory Interface, that capacity will grow to up to 4 terabytes and the bandwidth up to 650 gigabytes per second per processor. And the only difference, the processor is the same, the Open Memory Interface out of the processor is the same. The buffer chip may be different and the memory may be different, because in one case you're going for capacity at a at a reduced bandwidth of 320 gigabytes per second. On the other case, you're going for a reduced capacity, but still half a terabyte of memory, which is much larger than the high bandwidth memory capacity, and a bandwidth of 650 gigabytes per second, which is very comparable. So we do see this as the really a very good combination of bandwidth and capacity that the Open Memory Interface gives us. The Open Memory Interface also is smaller than direct attach, so there's more space on the chip to put more interconnect. So we get more bandwidth, more capacity with less chip area on the processor side. So there's more area left for other things. And the DIMMs are smaller too. I mean, this is what a standard JDEC DIMM for direct attached memory. This is a IBM Centaur DIMM for our old buffer chip technology. And this is an Open Memory Interface DIMM. You can see more or less to scale. The interface is smaller. The DIMM is smaller. This is the buffer chip that is developed by Microchip. And we have higher latency, higher capacity, and higher bandwidth, higher capacity, and only a very small increase in latency, about 5 nanoseconds from this to this, and a reduction in latency from the old Centaur DIMM to the new Open Memory Interface. So a small increase in latency, but much higher capacity, much higher bandwidth, which are key for supercomputing. The last technology I want to talk about is OpenCAPI, which is our open technology for system interconnect. It's a way to coherently attach devices to the processor at a very high speed. So coherency means that no, the processor can see the memory in the device coherently, and the device can see the memory in the processor coherently, and the application running on the processor can directly attach, address that memory in the device without no intervention of the operating system or supervisor or any other kernel during the execution. You need kernel support to establish the addressability, but once you have the addressability, you can just use that memory. So this can be used for multiple applications. Most recently, most of the applications have been some form of card that combines networking with processing. And they come from different companies, Mellanox, Nalatec, Alpha Data. They typically have an FPGA because we provided the IP to program the FPGA with the OpenCAPI interface. It could be an ASIC, but no, most tends to be an FPGA to do the processing, and then networking capability. You can see this, the Mellanox has 25 gigabit per second networking. This has 100 gigabit per second networking. These two also have 100 gigabit per second networking, and the FPGA sometimes have small, medium, or very large FPGAs, and they have their own memory as well. So you can have a processor, a system attached accelerator with lots of dedicated processing and lots of networking, and the processing can be done on the data as it flies through the network. The Nalatec is for network storage. The Alpha Data is primarily for computing, right? The machine learning, deep learning, inferencing, and the Mellanox is for network acceleration. Looks like I'm out of my time, so I just wanted to again say that we have delivered these three technologies in OpenPOWER. So they are open technologies for number crunching, memory bandwidth and capacity, and system interconnect. The matrix math assist instructions provide a new level of support for dense linear algebra and related computations. And OMI and OpenCAPI provide a new level of memory bandwidth, memory capacity, and system interconnect. All three are scalable. They have room to grow. We are nowhere in the limit of what they can do. And together with open source software, we see a clear road ahead for high performance computing systems that combine the best innovation from the community. Thank you very much for your time, and I'll be happy to take questions.
Thank you, Jose, for the wonderful and very detailed presentation on the OpenPOWER ISA, as well as the features of it and the power innovations. Thank you very much.
You're very welcome.
Audience, any questions? CINECA team?
I think that there is a question in the chat.
Yeah. Yeah. Jose, if you want, I can read out actually. Considering the bold move made by Fujitsu with the A6 4FX, did you consider moving memory and interconnect control on chip, at least for HPC focused products?
Sure. So my understanding of the Fujitsu machine is that they use HBM for the memory, which gives a very high bandwidth, and they use their own proprietary interconnect, the TOFU interconnect for the system interconnect. From our perspective, the HBM is of course a very high bandwidth solution, but with the caveat of capacity, right? So let me go here. HBM does give you a terabyte per second of bandwidth. I believe that's more or less what the Fujitsu machine has, but it also has reduced capacity. They're either 32 or 64. We need for our machines much more capacity than that. We see the OpenMI giving us that capacity, the 4 terabytes that no other technologies cannot give, but still giving us 2/3 of the bandwidth. And this is the bandwidth this is the bandwidth of the memory. The processor actually has more bandwidth. So no, there is room, like I said, there is room to grow. So we could eventually with OMI get to the level of bandwidth of HBM. And in fact, you know, even maybe have HBM, have a buffer chip that speaks OMI on one side and HBM on the other side. OMI is memory agnostic. It's made to evolve. So we can have DDR4, DDR5, we can have GDDR, we can have HBM, but directly attaching the HBM to the processor would not give us the capacity that we need. In terms of interconnect, I think it's the same story. I mean, I think the TOFU interconnect is fantastic. It reminds me of the Blue Gene interconnect, but our processors need a little bit more flexibility. We need to be able to attach other things like, you know, storage, or like I had in my, we need to have the ability to attach more versatile things that, you know, more than just an HPC interconnect, right? Power 10 will be used on a variety of systems, including HPC, but not only HPC. I hope that answers your question.
Yeah, thank you, Jose.
Is there another one? Oh, do you plan to extend the power SA with very long vector instructions like 512 or 1024-bit? We always look at, you know, what should we do in terms of improving our vector capability. We like the solution that we did here with the MMA because of something I mentioned before, the density or the computational density, right? It only takes, in this case here, I only need to load 128 bits here, 128 bits there. So I need to load 256 bits from the register. So probably I need to fetch. So I need to fetch 256 bits to do 16 multiply adds. If I were doing a 512-bit vector instruction, I would have to load 1536. I would have to load fetch 6 times more bits to do the same amount of computation, okay? So again, I fetch 256 and I do 16 multiply adds. A 512-bit vector instruction, like the Fujitsu machine has, needs to fetch 1536 bits, 6 times more to do the same operation. So we find our solution more efficient. Okay.
Any more? Thanks, Jose.
Thank you. Thanks, Ganesh. And I probably should move on. Thank you.
Yeah, I think, yes, I think interest of timing. Yeah, thank you again for your wonderful presentation. And let's move on to, you know, our next presentation from University of Oregon, Dr. Samir Shende, who is the TOW, you know, the performance tool founder, and also the performance director from University of Oregon, will be sharing his experiences on power systems. Dr. Samir, please go ahead.
Thank you very much for inviting me today, Ganesan. I want to discuss 2 different products. And the motivation for that is that with growing hardware complexity, it's really getting hard for us to accurately measure and optimize the performance of our HPC and AI machine learning workloads. And the second problem that we are facing is that as our software gets more complex, it's getting harder and harder to install our tools and libraries correctly so that they work well in this integrated interoperable software stack. And to address these 2 problems, I'm going to present the TOW performance system, which provides a portable performance evaluation toolkit, and it's available for download from this website. And the second component is the extreme scale scientific software stack, or E4S, that has a full stack of different software technology products from the Exascale Computing project. And it has integrated these different packages in a single distribution of a container. It's available for Singularity, Docker, and you can easily install it. And given time, I may be able to even show this working on the CINECA system, the Marconi 100. So here is the URL for E4S. Now, TOW is a performance measurement system. It has 3 different components. There's the instrumentation or adding hooks to your code, the measurement where we can create profiles or traces, and the analysis where we can view the performance data. And we support a number of different languages, including Python and C and C++ and Fortran, and support automatic instrumentation of these. And our measurement layer can support tracking of data for different runtimes, such as the MVAPitch2 runtime from the Ohio State University, a dominant MPI runtime. We have OpenSHMEM. We have other PGAS runtimes. We can also do instrumentation at the level of threads using OpenMP thread interface, the OMPT tool interface. We can track P threads. We can even do tracking of kernels executing on GPUs for CUDA, OpenCL, OpenACC, and we have support for both profiling and tracing. Was there a question? No, okay. So if you are wondering, what can Tau show you? It can show you how much time is being spent in different code regions at the level of routines, loops. It can show you the contribution of each statement, time spent in OpenMP loops, even the data transfers between host and the GPU, and the time spent in GPU kernels. It can show you, instead of time, it can show you counters from PAPI. These are hardware performance counters that can show you the floating point operations, level 1 and 2 data cache misses. It can show you the memory usage, where memory is allocated, deallocated, the memory footprint, the energy usage, the IO, and even how the application scales. But to do that, you need to add hooks to your code, and we can do this using a preprocessor, using a compiler, or we have a tool called Tau exec that allows you to preload a Tau DSO and then instrument the code for the runtime. And it supports both profiling as well as tracing, where profiling shows you the total time spent in the application at the level of routines or loops, and tracing can show you when those events take place along a timeline with timestamped logs. And using this Tau exec tool, you can see the time spent in MPI, OpenMP, even the IO and memory libraries. And then you can enable other options in Tau, such as event-based sampling or generate traces. And here is a quick start, which shows you that typically when you load a module for Tau on a system, you can just launch an uninstrumented application out with Tau exec and enable event-based sampling like this. Or use OpenMP tools interface, such as with compilers like Clang 9 on the IBM systems, and use Tau Python instead of Tau exec for Python workloads, and enable CUPT or the CUDA profiling tools interface and generate profiles or traces for third-party analyzers. Once you generate the performance data, you can launch the Paraprof tool and can show you how much time was spent in each code region on different MPI ranks. You can stack these bars separately and see the shape of each function. And it supports Python, MPI, CUDA. You can just launch the code using the Tau Python instead of Python and generate performance data that shows you the time spent in different Python routines. And even within those routines, you can see what kernels were executed and so on. You can click on a thread statistics column and sort data in different ways, and even go down to the source level and see exactly where the application was spending its time. We also have support for tracking the data transfers between the host and the GPU, and you can see along which call path the data transfers took place, and even go down further and see what was going on inside a particular MPI library. And in this case, I'm looking at the IBM's Spectrum Scale MPI library, Spectrum MPI, and see exactly what it was doing within the MPI bcast operation called by a Python function. We also support different modes of sampling the call stack, and we can even look at inside the Python execution at the level of the C++ code. And you can see the exact C++ kernel executing. And in most cases, you just need to launch a particular application using the event-based sampling flag and use uninstrumented binaries for profiling and tracing. You can see IO events, which show you the bandwidth and the bytes written to each file. And you can view all this in a 3D profile browser called Paraprof. And then you can see the MPI ranks and threads. You can see the functions and then the time taken in each of these functions. So you can see, for example, the shape of this function is opposite of this. And zoom into a particular location in this three-dimensional space and see the time spent in this function on that thread is 15.6 seconds. We can also see the communication matrix display, which shows you the senders and receivers. You can launch an application using a tau environment variable or generate traces that show you exactly what each rank was doing and sending messages from one to the other. We also support the Chrome browser, which many of you may have on your laptops already. And so you can generate traces that can be visualized using Chrome, using a workflow such as this. We support the Vampire trace visualizer, which is the state-of-the-art visualizer from TU Dresden in Germany. And you can see over here that Tau can generate OTF2 or the open trace format traces. And we support the COCOS profiling interface, which in this case shows you the execution of individual kernels, parallel for loops on OpenMP threads. And we have support for many different runtimes, such as the dominant MPI, pthread, OpenMP, OpenACC, including ROCm, COCOS, and Python with CUDA. And we can mix and match these. So you can have, for example, COCOS with pthread and MPI instrumentation. And you can just launch the execution with the Tau exec tool with different parameters. Now, to install Tau, there is an easy way to do that using the Extreme Scale Scientific Software Stack, or E4S, which is a community effort to provide open source software packages to simplify the development, deployment, and running of these applications on HPC platforms. And there are a number of different HPC packages, including MPI development tools such as Tau and PAPI and HPC Toolkit, and math libraries such as PETC and Trilinos, and data and viz tools such as Adios, HDF5. And they are grouped in different software development kits or SDKs for math libraries, data and visualization, programming models. I lead the programming models SDK effort in E4S, and it provides curated release of these software technology or ST products based on the SPAC package manager. And we create binary build caches for even bare metal installs. So if you're using SPAC and you can point to our SPAC build cache, you can download binaries of different packages and install them without having to recompile them. And we have support for full-featured containers with GPU support. We have recipes for creating your own custom base images, and these are hosted on GitHub. And we have a virtual box image and even support for cloud-based systems. And here I have a release of version 1.1 of E4S that includes over 45 different products. And you can download it from our e4s.io webpage and go to GitHub and download it from Docker Hub as well for PPC64LE like this. And here are the 46 different products from ECP software technology that are integrated in E4S. And this includes Tau and other tools such as Trilinos. And there is a Singularity image where you can download this image for PPC64LE. And this provides you a single image which has all these tools pre-installed, and they run on your IBM systems. We have support for GPUs, and it's all based on SPAC, which is the primary mechanism for delivering the software through the SPAC package manager. And the reason for using SPAC is that scientific software is becoming extremely complex, and the dependency tree of different packages is just exploding. And it's difficult for a naive user to download all of these packages, build them one by one, and get them to work in a consistent, integrated manner. So SPAC can help with this, and it's useful not just for open source software, but also for proprietary codes where sometimes they need other components that are open source and that can be provided through SPAC. And you can just clone this repo from the SPAC GitHub and then source it and install a package directly using SPAC install, such as tau, and it will build all the dependencies. So here is the naive installation, or you can say, I want a specific version of tau built with GCC version 7.3.0 and enable Python and MPI and pthread support, and say, instead of using the default MPI, please use the MVAPitch 2.3 version using the special dependency information like don't enable the wrapper RPath. And then SPAC find can show you what is installed on the system. And it just simplifies the installation of HPC software. We have these binary build caches that can support the installation of tools. And we have over 10,000 binaries in this SPAC build cache, so that even when you're installing software locally on your system, you can just point to this and execute commands like that. And it will just install the tools in your local directory, getting the binaries from this web site. And we have different images on Docker Hub as well. There's a TensorFlow 2.2 image that uses CUDA 10.2 for PPC64LE. We have base container images, which you can use to customize your own containers, and reproducible Docker recipes that you can all find on these web pages. And we are using it to build software using GitLab. We have a build pipeline for multiple compilers and architectures, and even a validation test suite to verify that the software is installed correctly. And we can then use this to create reproducible container builds using base images. And you can even try some images using VirtualBox image, where different runtimes like Docker, Singularity, Shifter, Charlie Cloud are all pre-installed. So we are working towards improving support for GPUs. We are working for integration of the DOE LLVM in E4S, and doing work in continuous integration testing, deploying it at various supercomputing centers, and improving the launch of MPI applications on full-featured supercontainers. So in conclusion, I'll say that Tau provides a versatile tool to measure the performance of these HPC and AI workloads. It's part of this bigger ECP E4S project, which provides a well-integrated software stack for AI, ML, and HPC workloads. And it's well suited for IBM PPC64LE platforms. It provides from source builds, which are assisted by this build cache of binaries for containers. And we have Docker and Singularity images available for download. You can download Tau from this URL. Our work goes on at the University of Oregon, and this is the Performance Research Laboratory in Eugene. Of course, the campus is bare at the moment, but this is how it looks. And I would like to thank our sponsors, the US Department of Energy and different DOE labs, the Department of Defense, National Science Foundation, NASA, CEA in France, and our partners, research partners from the University of Oregon, the Ohio State University, the developers of MVAPitch 2, Paratools, University of Tennessee, Knoxville, the developers of PAPI, TU Dresden, the developers of Vampire, and ULS Supercomputing Center, the developers of tools such as Opari and Scorpy. And thank the Exascale Computing Project for their sponsorship. And I have some time to show you a quick demo on the Marconi system at CINECA. I've logged into the system. I've allocated a single node, and here is the node that was allocated. I have SSH to this. And to give you a feel for E4S, so if I want to install all these different tools, I can just download a single image like this. This is the Ubuntu 18.04 GPU image for PPC64LE from the E4S website. And I can launch it with a singularity command. I'm saying enable the --nv parameter for access to the GPUs. Here is the image, and run bin bash shell. So if I launch this, now I will have a singularity shell where all these packages are pre-installed. And I can say spac find, and you can see all the tools such as tau, which are installed in this image. There are many Python tools as well. And I had enabled the --nv flag and turned on support for CUDA. And if I look at NVIDIA SMI within this container image, I can see that I can access the 4 V100 GPUs on the CINECA node. And if I say launch Python and say import TensorFlow, it's there in my path now. So I don't have to install a bunch of these tools and worry about how they'll be configured to use these GPUs. There's OpenCV, there is Keras. If I want to check, is GPU available? It is accessing the V100 Tesla GPU on the Marconi system. And you can see there are 4 GPUs. In fact, let me just go to this demo directory. And here is a sample classify MNIST example that would use the GPUs. And if I just run this and ask, what is this image in the file called image8.jpg? And it's running this, and it says that it is a 99% chance that it's a 3. And if I just open up this particular image, it is indeed a 3. So this is just a validation that it's working correctly. If I'm interested in looking at a C++ application like the molecular dynamics code CoMD, and if I want to compile it with MPI, now MPI is in my path and various packages are provided by SPAC, and I can just say make clean, make, and build this code with the -G flag and full optimization turned on. So here, if I go to the bin directory, move any previous data, and if I want to run the code, I typically run it like this. And if I want to run it with tau, all I have to say is, instead of using CoMD MPI, just launch it with tau exec, but enable the sampling with event-based sampling like this. And so I can just say rt.sh, and it will run this application, and it will run it on these MPI ranks. And then I will have performance data that will be generated that will help me identify where the program is spending its time. And so you have tools like pprof that can be used locally, or paraprof that can be used to pack the data and also view the data. And what I'll try to do is, here is the profile files. And let me just say paraprof pack and call it COMD ppc64le.ppk. And here, if I look at my home directory, here is the E4S directory, and I have this file here. So I can just SCP this file from the E4S directory on the ppc64le.ppk file and bring it over. And I'm just launching the paraprof tool locally. And there I can see exactly what is happening in each MPI rank. You can stack the bars separately and open up the thread statistics table. It says 29.3 seconds were spent in the application and 29.14 seconds were spent exclusively outside of MPI calls. And with sampling, I can explain 29.01 out of the 29.1 seconds. And here are all the samples that are collected. And it says that 27 seconds were actually spent executing this particular function called LJ force. And you can see all the functions that were executed and where they come from, with advanced velocity, LJ force. Here is a certain line number in ljforce.c. At line number 199, it spent 6.3 seconds on the first rank. Here I have downloaded a copy of this source code, so I can actually go down to this particular loop and see that it's in a for loop, this statement. And this for loop is within this second, third, fourth, 5 levels of for loops. And this is the line where it is spending 6.3 seconds. So you can drill down right down to the loop and the source line number with tau very quickly and say that these are the lines that are taking this amount of time in my code within these loops, and say, so this is the function called LJ force in this COMD application where all the work is being performed. And you can evaluate the performance of your code on a per thread of execution. And we can see that this was run on the Power 9 CPU running on at 3.8 gigahertz. So with this, I would like to conclude and see if there's any questions. The slides are posted on the chat window.
Thanks, Dr. Samir, for the wonderful and the detailed presentation on tau and E4S. And we have a question from CINECA. Is R also available as part of
R available within this particular toolkit? Well, we have some base images where it's easy to install R, and we have done this. So we can create an R-based distribution for you. But in the image that I just showed you, it was targeting the AI frameworks and HPC, and R is not in this particular image. Does that answer?
Sure. Thanks, Dr. Samir. And also, any other questions from audience? Participants as well as the panelists. Any other questions?
Well, thank you for inviting me.
Oh, thank you, Dr. Samir, for the again, for the wonderful presentation. And let's move on to the third presenter from IBM, Brian Allison. He's going to be sharing about the OpenCAPI features as part of IBM's advanced accelerator. Brian, Please go ahead and start your presentation.
Thanks, Allison. Can you hear me okay?
Yeah.
Okay. Let's see here. Can you see my screen? Oh, not yet. Hold on. Can you see my screen?
Yes. Looks good.
Which one are you seeing? Do you see an
industry background?
Okay, industry background. Yeah, thanks. Thanks for inviting me to present here, Jonathan. What I want to talk to you folks about this afternoon is a little bit more in depth about OpenCAPI as well as OMI. Dr. Jose at the beginning of the call was mentioning some of the features around OMI and OpenCAPI, which is also a little bit redundant with some of my pitch, but then there's other things that I'd like to at least bring to your awareness, I guess you could say. I'm part of the team, the development team here in Rochester, Minnesota, that was doing the OpenCAPI technology and architecture development. And so I'm very active in, let's call it the OpenCAPI work groups, as well as the overall ecosystem. Now, as part of that, I'm also very active in CXL, as well as Gen Z. So I have a pretty good lens or aperture of what's happening overall in the industry. So I can kind of compare and contrast, you know, IBM's approach around OpenCAPI, versus what the other approaches are in the industry, and what the strengths and weaknesses are, and things of that nature. So we can kind of broach on those things as we go along. And so if there's a question and answer on that, we can do that. So obviously, as I mean, you folks are very well aware, you know, out in HPC, out in research, right? The industry is just ripe with data, right? It's very data rich. The amount of data that's being collected either through sensors, you know, data acquisition and things like that. And we have just, you know, a slew of data, but we have, you know, a lack of insight with respect to that data. And so if you look at the proliferation of data that's being generated these days, it's just exponentially growing. And so, you know, our group, you know, and we have a kind of a ecosystem part of my team that runs out of the IBM Montpellier research organization is actually working with partners such as yourselves, trying to tackle, let's call it, their tough problems, because they have tough problems with, you know, I've got so much data, I've got bandwidth challenges with PCI Express Gen 3 or Gen 4, right? How do I go ahead and tackle these problems? So, you know, that's part of my organization's responsibility, is to work with folks out in the industry going, okay, let's start to tackle your problems, let's start to talk about them and see how we can apply the OpenCAPI technology and then the ecosystem around it to solve some of these tough problems. And a lot of the problems, you know, they're very extensible into, let's call it, specialized hardware, right? I mean, CPUs and GPUs have been around for a while, a long time, right? They tackled their respective problems very efficiently, right? I mean, if you look at what the GPUs can do today versus what they did 10 to 15 years ago, it's pretty incredible. And, you know, Jensen, give him credit, right? He spent $1 billion to basically get all of his ecosystem up to snuff, right? And he's basically reaping the rewards of it. So kudos to him, and everybody is kind of following suit. And specialized hardware is part of the equation. So, you know, we look at things like OpenCAPI, right? We look at, okay, there are other facets or other tough problems that need to go beyond just CPUs and GPUs. And we've got, you know, a couple of different relationships, probably pretty close to what you guys are doing, you know, with PSI or ESRF, where they've got tough problems where they're looking at, okay, I have to do things beyond just traditional CPU type acceleration. I need to do things beyond just GPUs. I need to be able to tackle, I got all of this sensor data. How do I, you know, pick the pieces out of the sensor data that makes sense, data prep it, feed it to a GPU, and then, you know, get an answer back. And so we're doing a lot of those types of dialogues with folks out in the communities. So that shouldn't really be a surprise to you guys. I'm going to kind of skip around in my presentation just based on what Dr. Jose was saying earlier. If you have any questions as I'm going along, you can feel free to please stop me, and I'm going to try and give you the whole kind of spectrum of what I'm seeing, just to kind of give you a lens on where I think the industry is going with respect to OpenCAPI and Gen Z and CXL. And so I'm going to kind of show you everything that I'm kind of seeing. Obviously, there's 3 typical use cases that are prime candidates for acceleration, whether you want to boost an individual function or a set of functions, you want to offload your CPU, free your network resources, or just basically be able to pick the pieces out of interesting information that's being collected from all these sensors. And we're seeing a lot of that, where FPGAs are doing a lot of that, you know, collecting sensor data, for instance, picking through the sensor data, prepping the data, and then feeding it to a GPU, collecting an answer, then feeding it back, right? So there's just basically a, let's call it a meeting of the minds, where you've got specialized hardware doing its most efficient tasks. So we've got, you know, a number of different engagements that are doing, you know, specialized hardware with FPGAs, with OpenCAPI. You know, they're looking at our, you know, our abilities to reach, you know, above 22 gigabytes per second across the OpenCAPI link. They're looking at our latencies that we're able to achieve around OpenCAPI. And they really like the advantages that those have. And so what we've done is, you know, for the last, let's call it 3 or 4 years, we've really, let's call it, maturized the technology. So if you look at the architecture specifications that have been generated around the transaction layer, the data link layer, things of that nature, as well as the PHY signaling and the, you know, the specifications are very mature. So, you know, the technology is at a place now where if you look at, you know, what we've got implemented in hardware and the ability to proliferate what's been developed over the last 3 or 4 years, it's actually, you know, relatively mature, right? Or very mature, where we're kind of at like the next step of the evolution chain. So we want to get into the mindset of, okay, how do we participate in the open ecosystem? And so, you know, you've probably seen all the recent announcements around the Open ISA, what we do with the microwatt core, what's been done with A2I, right? We are also, OpenCAPI is also doing similar types of initiatives where we want OpenCAPI not to be driven necessarily from the consortium itself or by IBM, but we want to basically have it participate through open source communities. And so we're using GitHub as our medium as far as proliferation of data, contributions that are being made by different organizations, as well as issue resolution, commentaries, things of that nature. And we'll go over that here in a little bit. One of the reasons to kind of take a look at OpenCAPI, I mean, IBM's been at, let's call it this FPGA acceleration play now for, you know, since around 2013. And to be honest, you know, our first implementation around CAPI 1.0 had some pitfalls around it, right? We weren't really able to achieve the Gen 3 bandwidth that we wanted to bring into play around that with CAPI 1.0. We fixed a lot of that stuff in CAPI 2.0, and we think we finally got it right with OpenCAPI 3.0. You know, it's not easy. It takes maybe a generation or 2 to get all of the technical requirements to meet into play. So if you look at what we can do today around OpenCAPI, right, we think we've got at least a 4-year head start on where CXL is today. I mean, CXL right now, if you look at where they're at with 1.1, you know, it's a very simplistic implementation around what they did with 1.1. They're at 0.9 revision status around 2.0. You know, you probably won't realistically see, you know, hardware associated with CXL 2.0, which is where I think it really starts to get interesting in, you know, maybe for another couple of years, 21, late 21, early 22. The interesting parts around, you know, CXL in my mind, and from what I'm seeing out in the industry, is not really around CXL.cache, it's around CXL.mem. We've got that running today with OpenCAPI 3.0 and what we call M1 mode. And so we've actually got an offering that I'll talk about here relatively in a few slides. It's called HMS, or Hybrid Memory Solutions. So if, you know, where I think things are going in the industry, I think most folks are looking at CXL.mem as kind of like the low-hanging fruit. I think looking at emerging storage class memories is very interesting. I think there's a lot of folks within the data center and cloud environments, you know, folks like, you know, Azure or Google, they're recognizing that traditional data center plays with just DDR memory as their overall footprint. There's extensions onto that where they have kind of hybrid memory tiers associated with that. They're very interested in looking at things around, you know, OpenCAPI 3.0 M1 mode. I'm seeing a lot of excitement around what Dr. Jose was talking about with OMI. One of the things that I see that OMI has an extreme advantage over CXL.mem is the latencies associated with it. You know, it's today, right? We're going to have these DDIMM memory buffer attachment mechanisms on our Power 10 processor roadmaps. You know, we've got a 25 gigabit signaling rate associated with that. But, you know, the memory buffer, right, itself can be, let's call it around a 10 nanosecond latency adder, above and beyond what you can do with just traditional DDR memory. CXL.mem, I don't think can get you there. From what I'm seeing, it's more of a, let's call it a tier 2 type interconnect technology. I think it can be, you know, a memory extension, but as far as being able to participate in the tier 0 or tier 1 memory topologies, I think CXL in its current incantation is going to fall short. It's going to probably take a future revision of CXL to kind of get there. And so, you know, it's one of those things you kind of got to look at the lens of what all the technical features are around all these different industry segments and all these different consortiums and find out the strengths and weaknesses of each one. I think Gen Z is very good as far as rack to rack or server to server interconnect. CCIX, you know, OpenCAPI and CXL are all doing acceleration within the server. It's my belief that CCIX is under significant pressure from CXL just because, you know, CCIX is being brought to bear pretty much by Xilinx. If you look at the participation within CCIX, that's gone down, you know, quite a bit. And then the participation within CXL has gone up. But, you know, one of the things that we've been doing is we've been developing over the last few years a framework around OpenCAPI. We did it originally around CAPI 1.0. We called it SNAP back in those days. We've actually done an implementation where we call it OCXL that supports OpenCAPI 3.0, meant to abstract away a lot of the complexities and do an FPGA development so that you don't necessarily have to write at the RTL level. You can write at the C or C++ level and use Xilinx's HLS tool chain stuff to compile it. And so we can do a lot of application development and acceleration in, you know, very insignificant amounts of time. And so we'll kind of go over that here in a little bit as well. Dr. Jose kind of talked about this earlier, but you know, one of the things that we like to say is we've got a lot of strengths in a lot of different areas around OpenCAPI, whether it's doing memory buffer design, right? Like we showed with the DDIMM form factor with microchip. Dr. Jose did mention it. It is an open industry standard. So if somebody else wanted to do an OMI implementation, they're really free to do so. That's one thing that's unique, I guess, around with respect to OpenCAPI versus CAPI. CAPI was centered around a power-based architecture. OpenCAPI is meant to be architecture agnostic. You know, so if you look at the specifications itself, you'll never see any kind of power designations within the architecture, whether it's in the transaction layer or the data link layer. So if somebody like an ARM or an AMD or somebody like that wanted to do an implementation around OMI, for instance, they're free to do so. And then you look at the architecture constructs behind it, right? It's written such that anybody could bolt onto their own fabric bus and have it work within their particular implementation. So like I said, I think we've got a lot of strengths around OpenCAPI with whether it's memory buffer design, whether we've got emerging storage class memories that are attached to an accelerator. You know, there's a lot of interesting things that are happening around ZNAND and other things like that, where, you know, they're looking at doing memory extensions, right? Looking at additional memory tiers and hoping to have interconnect topologies that support byte addressable, you know, load store semantics under a kind of a PMEM type construct, right? We believe we've got the ability to do that. We've actually got an offering that, like I said earlier in the call, that around Power 9 that we're going to offer later on this year. So why don't we just kind of talk about the different the different modes around what we got today with Power 9 with respect to OpenCAPI 3.0. We actually have the ability where the accelerator is the master of all the communications. So we call this AFU C1 mode, where the accelerator is basically in command of all of the acceleration and then the communication back to system memory. Then we actually have the other reverse direction, where we call AFU M1 mode, where the processor is doing load store semantics to byte addressable memory, where you actually have device memory behind it. And so what I'm seeing in the industry today is there's a lot of significant industry interest around CXL.mem around this particular paradigm. We've actually got this today around OpenCAPI 3.0 M1. And so this is something that's available today, and that we've got a number of different industry initiatives that are going around with respect to this particular mode. In fact, this is probably the most prevalent mode from that perspective. But then we've also got a number of different collaborations where, like I said, we've got folks with sensor data that's being, you know, collected out here, and they need to be able to ingest it at a very high bandwidth rate to do a lot of massaging of the data, you know, and prep it before it gets sent off to a GPU. So we've got a couple of different collaborations that are going on with respect to that. I mentioned this earlier, we're running at a 25 gigabit signaling rate. It's a by 8 implementation. It is an OIF standard. So if you look at what that is, today it's an OIF standard, so it's not PCI Express. It's mainly an Ethernet standard is what OpenCAPI is. So let me kind of speed this up a little bit since I've got 10 more minutes. Like I said, you know, the memory paradigms, we've got a lot of interest around doing different tiers of memory. So we're looking at, we have a number of different collaborations that are going on with respect to that. And then a lot of, like I said, collaborations around the needle and the haystack problem. We do have a server that IBM is offering. It's called the IC922, which supports OpenCAPI 3.0. We've actually got the ability to plug in 4 OpenCAPI adapters in this particular server. Dr. Jose was kind of mentioning this earlier. These are the adapters that we've got in play. Nalitech and Bitware and Alpha Data are the primary FPGA card suppliers that we've got in play, right? It's the connector is actually an Amphenol Slim SAS connector cable assembly, and so we've got both of these. We've actually got different initiatives with different partners using each one of these adapters. So those are the adapters that are in play. This HMS offering, this is something that's going to be offered around Power 9, I think the latter half of this year, maybe November, where we've got, it's meant to target SAP HANA OLAP workloads. It's got Samsung ZNAND memory. It's going to use PMEM as kind of its kind of constructs, which is industry standard, to exploit this type of memory. So, you know, we're also looking at providing solutions around exploiting storage class memories forthcoming later on this year. Dr. Jose mentioned this earlier around you know, having media independence. It's a lot easier to respin a memory buffer. You know, let's say you're going into DDR5 or something that might come from, you know, GDDR or some sort of whiz-bang thing that might be coming from some sort of memory vendor. It's a lot cheaper to respin a memory buffer, and then you can start to free up those pins on the processor package, and then start to free up resources on the processor and not have to spin those every single year every time you want to bring in a new type of media content. And so the value prop is basically, you know, folks like Microchip and others, right, can develop around this OMI standard to develop their own controllers to attach to OMI. You know, it's got significant memory bandwidth, a lot less processor pins, and obviously it's got lower solution costs to support that. The next set of slides, I'll kind of go through these quick, and we can actually have, you know, if you want to get into a deep dive around OCXL, the idea is, I mean, why would somebody want to program something at RTL level specifications around an FPGA accelerator when you can do it at a higher level programming language? Especially if you can do something that's like in the 2 or 3 weeks where you can actually get something that's relevant on the outside of it versus spending, you know, let's say 3 to 6 months trying to develop it in RTL and getting it through the tool chain flow. And so we've done a number of different examples with our programming framework around OCXL. The idea is we don't want folks to worry about the constructs of the plumbing, whether it's HBM memory, whether it's Ethernet, whether it's the OpenCAPI IP. We kind of abstract all that stuff away. We want folks to really worry about their application and their accelerator. I don't know, think about a sponge algorithm, think about some sort of network encryption, think about, I don't know, dedupe something, whatever, right? The idea is focus on the accelerator. Don't worry about the plumbing. We'll take care of the job scheduling, the task management, the processes, all of those things. You worry about the accelerator, we'll take care of the rest. We've actually open sourced all this stuff, our implementations. You can actually go out there and take a look at it today, download it, kick the tires, you know, get a look and feel for what it is. It's on github.com/OpenCAPI. That's where all of our open source contributions are made. So you're going to see, and we'll talk about that here in a few minutes, but this is where OCXL is done. Like I said, we want you to worry about the actions. We'll take care of all the plumbing. We'll take care of all the scheduling. And it all runs on top of Vivato's HLS. So I have a couple more minutes. One of the things that we're doing or we're working on is to get a cloud environment kind of stood up at Nimbix. So we want developers to have the ability to run OCXL, the programming framework, the simulator, try out our examples and things like that in a Nimbix cloud environment. It's not stood up yet. We're still working on that. You can actually do it around Power 8. So if somebody wanted to test out CAPI 1.0 using Snap in a Nimbix cloud environment, they could do that today. But we're looking at doing an integration around OpenCAPI 3.0 in the future, right? And, you know, if you could spend, you know, 30 cents an hour versus, you know, having to deploy your own, you know, that might be something for folks to kick the tires on. Let's see here. Yeah, I mentioned this earlier in the call. One of the big things that we're doing, and it's a fundamental shift within IBM, is to basically get out of the business where we're the champion of everything. We still want to be a leader in it, but we also want, you know, the ecosystem to evolve and to maturize around open source communities. So we've done a number of different open source contributions on GitHub. There's a few reference designs. Obviously, when we did our microchip development for the memory buffer, that wasn't there on day one. So what we actually had to do to test out our processor was to create FPGA implementations around a device side, much like a memory buffer is. So there is an OMI device side FPGA reference RTL that we posted out on GitHub that looks like a microchip memory buffer, but just a more simplistic form. And then we actually create a host side implementation as well to test out the memory buffer. So you'll see that that's called Fire. That's the host side based OMI based implementation. ICE is the one that's the device side implementation. And then we've got the OpenCAPI 3.0 and that supports M1 and C1 mode that's been posted out on GitHub. We've also posted out there an OpenCAPI simulation engine which allows you to basically simulate your accelerator plus the application. We've got OCXL, which also embodies the OpenCAPI simulation engine, as well as the user level API libraries. All that stuff is underneath github.com/OpenCAPI. It's got an Apache 2.0 licensing model. And it's free for you guys to basically download and start to kick the tires on. I mean, we want folks to get the look and feel of it without actually having to go through IBM. If it's interesting to them, obviously they can take the next steps. We can actually have the next set of conversations. And then from there, you know, if there's contributions that you want to make back or what have you, right? That's what the spirit of innovation around open source communities looks like. If you look at our reference design, it's very lightweight as far as the implementation on the FPGA. It doesn't take very much FPGA resources, you know, at the most, maybe 6 or 7% on a very relatively modest sized FPGA, the VU3P. I did mention this earlier. We've got the simulation environment that we've posted out there. We've also posted out there some exerciser examples. These are the same exerciser examples that we used as part of our processor validation. We've got an OpenCAPI M1 implementation. That's what this memory home agent is. We've got a memcopy, which is a C1 implementation. They're all open examples. They're free for you to download if you want to use them, steal them, borrow constructs of them, whatever, right? That's up to you. And then I think the last thing I just wanted to kind of mention was, you know, here are some of the constructs or some of the performance metrics that we've seen around OpenCAPI, right? We're able to achieve around 22 gigabytes per second, which is right on target of where we want to be. We want to be around 90% efficiency, and we're basically there. So the implementation is pretty solid. It's very solid, I should say. This reference design is the same reference design that we used for when we did our processor validation. So it's tried and true, and so we donated it out there because we want other folks to leverage it as well. And that's actually the last of it, Jonathan. I know I spoke pretty fast, but.
Yeah, Brian, thank you very much for the detailed OpenCAPI presentation. You know, it's very good. Audience, panelists, any questions for Brian? Dear CINECA team, any questions? Yeah, we have a question from you know, CINECA, Brian, on the question Q&A window. The question is, do you have some partnership with GPU vendors to use OpenCAPI with GPUs?
I think the question is well, there's two ways to answer this question. So we don't have a partnership with, let's say, AMD or NVIDIA to have OpenCAPI as their interconnect. Both of those companies, if you're a part of CXL, you will see both of those companies are part of the CXL consortium, right? That's basically where they decided to lay their bet as far as interconnect topologies. What we've done though is we have the ability to share, you know, virtual memory, right? So we can still be able to move data back and forth very efficiently between OpenCAPI and the GPUs, even though it's on a different, you know, it's on NVLink, right? So with NVLink today, we're actually able to participate in the same shared virtual memory constructs, and we've been able to do that very efficiently to move data back and forth. Even though they're not using OpenCAPI as the construct for today, with NVLink we can do that. But moving forward, both NVIDIA and AMD have basically said that they're going to use their CXL constructs. Now, to be honest, CXL.cache from a GPU implementation does, you know, if you look at the architecture itself, and it'll be obvious if you study it well enough, there are some significant things that need to be addressed from a GPU perspective, right? We had to address those when we did NVLink the first go round. And so I think you're going to see probably some evolvement around CXL to address some of the GPU challenges, let's call it that, as CXL moves forward in time. Because even CXL 2.0 today has some things that aren't the best suited architecture constructs for a GPU implementation. I'll just leave it at that.
Thank you, Brian. Any more questions?
Yeah, I have a question, Brian. If so, I'm Argyo from UW Platteville. First question is like I recently got a IC922 system and also a Raptor system, which has some OpenPOWER things in it. So
Sure.
I mean, how can we set up this OpenCAPI on those boxes?
I'm not sure that the Raptor box has that capability
Okay.
yet. Is it a Blackbird? Is that what that is?
Yes, I mean it's just it's a Power AI optimized machine. I'm not yeah.
Okay. So what we should probably do though is just after the call, we should probably Goddison should just give you my email, or we can probably just set up a separate call, and then we'll start to kind of get those conversations on how you can get your OpenCAPI stuff kind of tested out on your IC922. That's probably the best way to do it.
Okay, perfect.
Just to schedule a separate meeting.
Brian?
Sure. Yeah, thanks. And one more question on this CAPI and OpenCAPI. I mean, do you have any benchmark or something like what type of applications? I mean, is there any specific type of application that can get major benefit from this type of hardware or this type of protocols?
Sure.
Like, let's
Sure.
say
We can show you those examples too in that same meeting. Yeah. We've got.
Okay.
Yeah, we can show you some of the examples that we've done with folks out in industry. And most of those folks are very willing to share. We've got data that we've collected with PSI, as well as ESRF and some others that are willing to share the work that they're kind of doing as far as the results that they're seeing. So yeah, we can kind of show you the results that they've been achieving and kind of the workloads that they've been doing, and where we think that OpenCAPI can show some significant benefits.
Great, sounds good.
Yeah, we can certainly set that up. No problem.
Yeah,
sure.
Brian, I will connect you with Professor Agia. Thank you very much for the presentation, Brian. Thank you.
All right, thanks, guys.
Yep. Audience, let's move on to the the next presentation. The next presentation will be done by Dr. D.K. Panda from Ohio State University, and he is going to be sharing experiences with working with the distributed deep learning and the special MPI, some of the use cases too. Mr. Panda, please go ahead. Start your presentation.
Sure. Just 1 minute. Okay. So can you people see my slides?
Yes.
Okay.
Mr. Panda.
Please go ahead.
Yeah, yes, Mr. Panda, we can see your
Okay. So again, hi. Thanks to Mr. Ganeshan for inviting me to give this presentation, this workshop. So today's the title of this talk is Scalable Distributed Deep Learning on Modern HPC Systems. So I'll be trying to show some of the experiences, what we have done with respect to deep learning and combining with our MPI, which is the MHPIS2 library, and trying to get a very high performance and scalable training on all different kinds of systems, including the OpenPOWER systems, like taking, I'll show you some numbers from the #1 summit system, the Allison, and which is very similar to the CINECA systems also. So at a high level, you can see like most of you must be familiar, we are in a very exciting phase. I mean, this is the big area of the artificial intelligence. Then within that, we have machine learning. And within that, we have a subset, which is called the deep learning. So traditionally, if you think of the machine learning, used to be like you have a set of inputs, you do some feature extraction, then you do classification, and then you generate the output. But now what we are trying to do, this feature extraction and classification is being combined together in the deep learning framework. So that if we have a given set of data, so let the machine try to learn the things, and then we can try to train it properly so that if we give a new input, we should be able to get the proper inference. So then this has, the deep learning has two phases. The first one is, as I said, like the training and the inference. And especially this training is the most compute communication intensive process. And this can take days to weeks. If you go back like a few years, people were talking about months, but now people are talking about days and weeks. The goal is like, can we try to reduce it to even hours or minutes? And in that case, if we can do that, such a faster training, obviously people can explore newer applications, newer models where deep learning can be used. So obviously when the hardware keeps on changing, we have newer and faster hardware. Obviously the training can be done faster, but there is of course a limit. If you are trying to run it, let's say on a single node with 1 GPU or 2 GPUs or 4 GPUs, still there is a limit. So the question is, can we try to use parallel and distributed training? So this slide tries to summarize the challenges. So what we want is both scale up and scale out. So that means these days, if you see some of the nodes like a Summit system has 6 GPUs, Lassen or Sierra or even the Marconi systems have 4 GPUs each. So can we keep on extending or trying to use more and more GPU within the node? So this is where like a lot of improvements are happening with NVIDIA CUDNN, Intel MKLDNN, etc. But then the question is, how do I scale out? That means if I want to use like 1,000 nodes with 4 GPUs, how do I scale to 6,000 GPUs? So this is where the different kinds of communication underlying systems are happening. Some community is going through the traditional Hadoop, even Spark route. Google introduced the gRPC, NVIDIA introduced the Nickel. And what I'll be trying to show that how you can try to achieve this through MPI, because MPI has been there for many years, and MPI libraries, as you know, runs on almost all the HPC systems. So the question is, why should we go through other approaches if the same MPI library can actually help you? So in fact, that will help also in convergence. That means in the same software stack, you can run your traditional HPC application as well as your AI application. So the broad challenge I'll try to focus here is, how do you exploit HPC? How do you efficiently scale out a deep learning framework and take advantage of the heterogeneous high-performance computing resources? So when I say heterogeneous, both like a CPU and GPU. So let's take an example from what is happening in the field, and I'll try to introduce that through TensorFlow, which is a very common deep learning framework. So over the years, so if you start like from the TensorFlow, originally it used to be the underlying communication runtime used to be the gRPC, that is the Google RPC. And that was not scaling very well. Then people went into this gRPC plus X. So that means some amount of communication you actually pass it through MPI, some through gRPC. Some people even propose solutions to directly utilize verbs. Then once the GPU direct RDMA came, some people tried to have these kind of solutions. But again, each one of these had some limitations. So now people have started moving to this no gRPC solution. So that means if you have like a underlying the Horobird ecosystem has developed over through Uber had proposed this many years back, and this is gaining a lot of momentum. I'll show a lot of performance numbers with that. So now with the Horobird underlying it, you can actually link it with MPI library or the Nickel library. So it gives two options. So either you go through the NVIDIA's library, you install it and run, or if you have already an MPI library installed, you should be able to directly take it through and run your TensorFlow without any issues. So in this context, let me introduce the project, Hpc project. This project I've been leading in my group. Almost now we are in the 19th year. Many of you must be familiar. We started this project almost the day one of InfiniBand. When InfiniBand was introduced in October 2000, prior to that, we were working on the MirrorNet at Quadrix. Those were the proprietary interconnects. So when InfiniBand came in, we were the very first team in the world to jump in and trying to see how you can design a high-performance MPI library for InfiniBand. And in fact, we had a first open source version demonstrated at Supercomputing 02 almost 18 years back. And over the years, we have been growing with the MPI standard, growing with all the different platforms, Interconnect. So currently we support not only InfiniBand, Omnipath, Ethernet, Rocky, when we have the AWS EFA solution also. Today, I'll be mostly focusing a lot of results with OpenPOWER and GPGPUs with NVIDIA. We have just started working on the AMD solutions will also be coming out very soon. So you can take a look. If you're not familiar, you can take a look at this website and visit there. Currently, these libraries are being used by more than 3,100 organizations in 89 countries. Just from our website, as you can see the number, we are coming very close to 1 million downloads. And it is not just the downloads. During the last 15 years, we have been enabling a lot of top 500 clusters to get the performance using our library. And so these are like some of the examples. I'm actually a partner in the 8th ranked attack Frontera system. It has like as you can see, 500,000 cores. This is the number 4th system in the China, 10 million cores. So these are the kind of systems are trying to take advantage of the MapHisto library. So this traditionally, of course, we started this with HPC applications in mind, but now what we have done, we have developed a new ecosystem which can provide you the MPI-driven infrastructure for your ML and DL training. So as I was telling earlier, the Horoword, this Horoword has links to MPI. So what we have done, I'll go into this more details. We have different versions of our MapHisto library, and we have interfaced this with the Horoword. And on top of that, now the Horoword, you can run TensorFlow, PyTorch, or MXNet. So if you are using any of these frameworks, you don't need, and if your underlying MPI library is installed, you don't need any other library. You should be able to directly utilize this, framework. We have a second project, we call it High Performance Deep Learning, HIDL. So if you go there, you should be able to find out the exact instructions, how to download this, how to configure it, and how to make it your entire MLDL ecosystem running with the MapHisto library. So let me go into these details. So what I'll try to show you some initial numbers with MPI-driven deep learning using our MapHisto library, both for CPU-based deep learning and also GPU-based. So those are the basic solutions. Then I'll also try to focus on, as the models and data sizes are increasing, there is a bigger issue which is looming, which is called out of core. So that means you cannot fit all the data and the model within a GPU. So how do you carry out the DNN training? So in that case, we have been exploring a lot of newer kind of parallelism. Traditionally, people have used data parallelism, but we are trying to go through model parallelism and hybrid parallelism. And using that, I'll try to show you a real use case from a medical. We have been working with some pathologists. I'll try to give some solution on the AI-driven digital pathology. And in addition to the OISU solution, I'll also include, we have a commercial spin-up. I'll also talk about that, and I'll try to indicate how you can actually get commercial support for our solutions, not the basic solutions, but very advanced solutions with a lot of introspection. For example, when you are running your DL application, how do you know where your performance is being lost, and how you can actually detect that and trying to provide some good solutions to alleviate that problem. So let me first start with the CPU-based deep learning. So this is where I'll try to use, we have a lot of different versions of the MapHisto library. So these are the MapHisto and MapHisto X I'll try to use for CPU-based deep learning. So here, let me try to show some basic performance numbers on OpenPOWER. As I said, for the last many years, we have been supporting OpenPOWER. If you have our OpenPOWER, you should be able to download our libraries and run it. So here I'm trying to show some performance number with our MapHisto X and also the Spectrum MPI. This is the version where we had done the comparison. So this is trying to show intra-socket small message latency, that within the one OpenPOWER, within the same socket, how fast you can do MPI level communication. So as you can see, we are able to communicate with only using 230 nanoseconds. We can actually communicate. This is half of round trip. And as you can see, as the message size increases, we are able to do very good compared to Spectrum MPI, because we have some advanced designs here in the MapHisto X version. This is not there in the MapHisto basic version. If you use that, you should be able to get very good performance for small messages, large messages. And bandwidth wise, we also try to deliver very good performance here at the within the medium message size. Internode, we are very similar. We lose out a little bit to Spectrum MPI, and we are trying to optimize that. Might be in the next release, we'll be able to come very closer. And bandwidth wise and bidirectional bandwidth, we are very similar, or a little bit in the middle message size, we are able to deliver better performance. So those are the basic point to point. But as you know, a lot of these deep learning applications heavily use collectives, and especially the all reduce. And this is what we have been trying to optimize in our MHPs2X. We have a special module which you use called XPMEM. So if you use that MHPs2XPMEM, that is the black line. So as you can see, like compared to all other libraries, we are able to deliver in a much more bigger fashion, like a 2x performance benefits, 3x, 2x, 48% benefits to optimize this all reduce, and that can actually benefit you to run your DL applications much more efficient. So here, let me try to show you some performance numbers. This has been taken on an x86 platform, not OpenPOWER, but you will see the similar kind of a trend. So this was like this we presented 2 years back at the IPDPS 2018. So that time we were comparing with Intel MPI, our basic MHPs2 version, but this blue line, a bar, you can see this is the MHPs2X version with the XPMEM support. So at a CNTK AlexNet training, we are able to accelerate, in fact, giving performance by 20% or 9%, even on a small scale environment. This is a number which is taken on a very large scale. This is from the TAC Frontera. Here you can see like this is a pure CPU system, and it shows the benefits of our MHPs2X library for CPU-based training. So here we have taken like the TensorFlow on 2,000 nodes. So this is 56 cores per node. So you can see like almost 100,000 cores, 110,000 cores, and we are able to get very good performance, even coming very close to the ideal number. And we are able to get like a 260,000 images per second. So if you want to train it, testnet 50 can actually be trained in just 7 minutes. In fact, many people think that GPUs are the only way to carry out the DL training, but that may not be the correct. So if you have even the pure CPU-based systems, you should be able to utilize the MPI libraries and get this kind of performance. And below a lot of slides, I am including the conference and the workshop papers where we published all these results. So you should, you are welcome to take a look at those and to get more details. So now let me go into the more GPU-based deep learning. This is where a lot of people have been focusing. So we have a very optimized library called MHPs2 GDR, that is GPU Direct RDMA. And this idea came, in fact, some of you might have heard of these terminologies in the community called CUDA-aware MPI library. In fact, we introduced from my group this terminology in 2010. We had a paper at the ISC, and we introduced this concept. So the broad idea is that, let's say you take a look at this kind of configuration. We have a node, and we have GPU, we have InfiniBand. So if I want to move some data, what happens typically, you try to do a CUDA copy, CUDA mem copy, and then do MPI send, and you do a other end, you do an MPI receive and CUDA. Some advanced users try to do things in the pipelining, but then that doesn't lead to very good productivity, because a lot of application scientists are trying to now go into and trying to optimize the data movement instead of focusing on their application. So what we introduced, the idea that can you directly send data from device buffer and receive in the device buffer? Okay, so from an end user perspective, you don't have to even touch CUDA. That's why we say like it's a CUDA-aware MPI library. So if you see the animation, you just do as an end user application developer, you try to say MPI send from this side, receive it in the MPI receive on the other side. And that's all you need. And inside the MHPs2 library, you can actually try to find out the optimal path, optimal protocol, and move the data in the best performance. And that leads to high performance and high productivity. Of course, we introduced this idea in 2010. Over the years, a lot of other MPI libraries have also taken the similar ideas. So we have been like taking, since the MHPs2 GDR we introduced many years back from 1.8 release to the latest 2.34 release. Not only we exploit this GPU Direct RDMA, we take advantage of IPC, we take advantage of data types, unified memory, even GDR copies, all the advances we incorporate in our library. And now if you take a look at the number, so this number is trying to show GPU to GPU, like GPU from one node to the GPU of another node, we can send data in just 1.85 microsecond. Okay? So if you look at the basic InfiniBand number, these are like 1 microsecond. So in another 850 nanoseconds, we are able to move data from one GPU node across the network to the other node. And that also leads to very big benefits in the bandwidth and bidirectional bandwidth. And I'm very proud of my team who designed these designs, internal designs. And these are some of the best numbers you can see in the world with any MPI, GPU-based MPI library. So those are some of the x86 numbers. So let me show you some numbers with OpenPOWER. This is from like any of your like Summit system or Allison or even your Marconi system. You will be getting similar kind of performance. So here it is a intra-node latency. That means using GDR copy, you can actually move data from one GPU to the other GPU within the node in just 760 nanoseconds. Okay? And then we have a very tight integration also with NVLink 2. You can get actually like a 65 gigabytes per second. And inter-node, here you go like a 2.18 microsecond. OpenPOWER platform has a little bit overhead compared to x86. So that's why we see 2.18, not 1.85 microsecond. And here it was like the inter network is 2-port EDR. So we are able to get like a 23 gigabytes per second. So if you have any OpenPOWER platform, you should be able to just download our library and you should be able to get this kind of performance. So those are like the point-to-point numbers, but then the question is, how do we optimize the collectives? And this is the collectives, as I indicated earlier. We have been doing a lot of optimizations in the collective. So in fact, in some of our designs, we use the GPU kernels themselves to do these kind of reductions. Okay, so think of like an all reduce is a computer operation. Many times, if you have the data in the GPU, people take it to the CPU and then perform the all reduce. So instead of that, we actually introduce kernels to launch kernels to do the all reduce where the data source lies. And now you can see this is trying to show some numbers on the DGX2, that is a NVIDIA machine, a 16 volta GPUs, and NVIDIA's library is the Nickel 2, that's a Nickel 2.6. So as you can see, for our MPI library is able to deliver like almost 4.7x better performance here for large messages, like we are able to give in fact 2.5x better performance. So then we try to scale it to this is the number 2 system now. It used to be the number 1. This is the Oakridge Summit system, is the OpenPOWER with 6 GPUs. So we scaled it to carried out the experiments up to 1536 GPUs. And the same trend you see, this is our latest release, MFP2 GDR234. You can see for all the different message sizes, we are able to get 1.6x better. Bandwidth, we are able to deliver in fact better. And for a typical message like a 128 megabytes message, which is very common in the DL frameworks, as you can see the red bars, the bandwidth, we are able to give 1.7x better performance. So all these algorithms have been designed with very optimizations in mind. So in fact, we just presented 2 weeks back a paper in the ICS 2020, and that design is already incorporated and made released in the MFP2 GDR234. And as you can see here, even Spectrum MPI, OpenMPI, Nickel, nobody is able to actually beat or come closer to the performance of the MFP2 GDR library. So this is trying to show another like a DGX2 not the earlier slides were at the all reduce, but now let's go into the to the DL application. So here it's like a running scalable TensorFlow is a ResNet 50 training. So again, you can see this is just 16 volta GPU. This is a DGX2 node. We are able to perform better than Nickel 2, and we are also able to get very good scaling efficiency as the number of nodes are increased. So then we ran this distributed TensorFlow. This is one of the best numbers we have obtained so far. So this we ran distributed TensorFlow on 1536 GPUs on Oakridge Summit. And again, this is comparing the Nickel 2.6 and the Nickel was not able to even run in a stable manner beyond 384 GPUs. Rather, we were able to go even up to 1536 GPUs. And here we tried actually ImageNet 1K, not the smaller one. It has 1.2 million images. And here we are able to get almost like a 0.42 million images per second. And now you can see that you can actually, with 90 epochs, you can actually train this ImageNet 1K in just 4.5 minutes. Okay, so that is the kind of a state of the art. You can see this is only using 1536 GPUs. We have not got access to go into very large scale Summit system yet, so thus we have not been able to run it to all the largest 24,000 GPUs. But if you can scale it, because the MPI library scales, you should be able to even reduce this to even faster and better numbers. So this is those are the TensorFlow numbers. These are some new numbers we have taken recently. This also we presented at the ICS paper. We are scaling PyTorch because PyTorch is also getting a lot of momentum. Now the similar kind of stories you see. In fact, for PyTorch, we are able to compare to the latest Nickel 2.6. We are able to give even 30% higher performance in terms of the images per second. So higher it is better. So then TensorFlow has recently, some of you have been following, are coming with a TensorFlow 2.1. So this we did some initial evaluation, even with comparing with the latest Nickel 2.7, which was released a few weeks back. And this is a Livermore's Allison system, which has 4 GPUs per node, OpenPOWER. It's very similar to the Marconi system at the CINECA. And there you can see again, we are able to beat the latest version of the Nickel and deliver better performance. And then recently, all these earlier ones are with the Horobot. And now there is a newer framework which is coming called DeepSpeed. Some of you might be familiar. This is getting a lot of momentum. So this directly, you can actually run with the MPI library. So what we have done here, comparing with Horobot without MWPIS2 library and then DeepSpeed, with MWPIS2 GDR library and DeepSpeed with MWPIS2 GDR. So now you can see that even the DeepSpeed is able to even deliver better performance compared to the standard Horobot. So these early results are promising. So this is just very recent results, just last 48 hours, we have got these kind of numbers, and we'll continue to work around this. So those are some of the basic things, but now if you start moving, as I said, there is a bigger challenge which is coming called out-of-code training. So that means if you take a look at these are the different kinds of models, as model sizes are increasing, even Volta GPUs, if you take a 32 gigabytes, if your model plus data exceeds that amount, so how do you carry out this training? So that is the bigger challenge, which is called out-of-code training. So what we have used is, we took some concepts from very old days of HPC, some of you might be familiar, called out-of-code sorting. So that means if your data cannot fit into the memory of a single node, how can you do sorting of large scale data? So there some concepts used to be like, how do you move data from virtual memory to the physical memory? So here we have done similar kind of thing using the unified memory concept. So as you can know, in a DL framework, there are multiple layers. So you don't have to bring all the layers to the GPU at the same time. You can only bring some layers. As the computation is moving, you can start doing some prefetch. And after those operations are done, you can move that back to the main memory. So using that kind of ideas, we have started a newer direction. And we have come up with in fact, together with that, we have a newer hybrid data and model parallelism. So this picture is also trying to show, if you see with the different image sizes, with the amount of memory is available. So as you keep on increasing the input image sizes, you take a Pascal GPU, Volta, Broadwell, CPU Skylake. Beyond these, you cannot do data parallelism. So you have to stick with model parallelism, and then we have a hybrid parallelism which distributes the data. And this paper we presented at the ISC a few weeks back. You can actually, there's a copy available in the archive. You can take a look at this. And using that model, also different results. So this is a CPU-based results where we are able to the framework is called Hyperflow. And we again took the ResNet 1001, and you can see on 512 nodes on the TAC Frontera, we are able to get 512 nodes, we are able to get all 481x speed up. Even on a 256 nodes, we are able to get 253x. So as the CPU cores are you have large scale accesses, you should be able to utilize this framework to get very good training. And then we took it into we started working with some of my colleagues here in the digital pathology. As you know, the pathology is being used in a lot of disciplines. Pathologist reviews a slide, carries out the diagnosis based on prior knowledge and training. Experience matters a lot. So the question is, can deep learning be used to train thousands of slides and let the computer carry out the diagnosis narrow down the diagnosis, and help the pathologist to make a final decision. So that has significant benefits in reducing diagnosis time, making pathologists productive, as well as reducing healthcare costs. So we have been working, so this is trying to show an example. So like they call it like an image slide. It has 100,000 by 100,000 pixels. It cannot fit into a single GPU memory. So we did some tiling and used our model parallelism and look at these numbers. So this is running on an OpenPOWER NVIDIA Voltage GPU. The pathologists were using even a single node with 4 GPUs. It was taking them 7.25 hours. And using our schemes, we were able to scale to 32 nodes to 128 GPUs, and we reduced the time by 27 minutes. So almost like a factor of 15 benefits we are trying to show here. And in fact, this paper just got accepted to the Supercomputing 20. So we'll be presenting more details on this at this conference. So it shows the powerfulness of our MAPIS2 library with the enhanced hybrid parallelism can be used to accelerate the deep learning framework. So those are on the things happening on the OSU side. Let me take a few minutes, try to introduce. We also have like a commercial support and products. So we have a commercial spin-off called XScale Solutions. So it provides a lot of services for end users, different supercomputing centers to optimize all these libraries, to get periodic updates. And in fact, through this effort, currently we are supporting two large supercomputing center. One is the Lawrence Livermore National Lab, and the second one is Kisti, Korea. So we are able to provide, just like any other commercial software stack, we are able to provide the services here. We are also a part of the OpenPOWER Consortium. We are a Silver ISP member. So that gives us a lot of leeways to work with the OpenPOWER ecosystem. So we can actually participate with different vendors for bidding, installation, deployment process. So as a part of this, we have introduced two products. One is called XScale HPC and another is called XScale AI. So this XScale HPC, again, if you remember, like Professor Samir Sande indicated, nowadays it's becoming so complex to install all the different libraries. And so here, it is not just the building, or it's also how do you tune it for all different platforms. So we have been working. So this is, if you download this or use this package, it's all out of the box fine-tuned. And just on a single build, you should be able to get the best performance. If anybody is interested to use this kind of thing, please contact us, and we can send you a version for a free trial. Now, we are focusing a lot on the second one, which is called the XScale AI product. So this is what I indicated earlier. So this has the integrated package with TensorFlow, PyTorch, MXNet, Horoward, and the MAPIS2 libraries targeted both for CPU-based and GPU-based deep learning. So what recently we have done, not only just the basic performance, so the question is, if you are running a deep learning job on very large scale system, how do you know, or how can you have some integrated profiling and introspection? Can you actually see what is happening at the Horoward layer? Can you see what is happening in the MPI layer? Can you see what is happening in the InfiniBand layer? If you get all these information, you can actually see where you are losing the performance and then trying to optimize. So we have a very deep profiling and introspection support. So it is available for both OpenPOWER and x86. You can do a one-click deployment and execution. This is also available for a free trial. Let me show you two snapshots so that you can see how powerful is this. So this is like a, we are trying to have this as your profiler. If you run your application, like let's say TensorFlow you are running, it exactly telling you all the different MPI calls, NICL calls, what is happening, how much time is being spent. You get the input either as a command line input or a JSON format. And you also get a dashboard, and it tells you all the information in the single dashboard. So here it says I'm running a TensorFlow with a ResNet 50. I'm getting 300 images per second. It is using 8-volt GPUs within MPI reduce. It is a lot of buttons. You can play around and see the numbers. And more important is here you can see that how many all reduced messages were introduced. And you can see that here the number of calls were as the message sizes. So around like 8 million message sizes, there were a lot of calls were made. And similarly, you can say like there is a 18 million megabytes of messages, a lot of calls were made. And in fact, the performance is also not good. So that gives you an insight saying that is your weakness point, and you should be able to go and optimize this to improve your performance. So like this, you can try to look at all the different calls. These are some initial capabilities we have provided, but more capabilities and features are coming. And the whole idea is that as an end user working with the systems folks, you should be able to totally optimize your entire software stack from the InfiniBand layer to the MPI layer to the robot to the TensorFlow to your end application, and try to maximize the performance from your system. So if any one of you are interested, again, please feel free to contact us, and we'll be very happy to work with you to have deployment of this product on your system. So with this, let me conclude. So what I focused here is scalable distributed training is getting important. It requires high performance and middleware designs while exploiting the modern interconnects. I provided a lot of solutions. The bigger focus is that these solutions just requires MPI. You don't need any other software stack. Yeah, as long as you have a high performance MPI like Megabytes 2 running on your system, you should be able to not only handle your traditional HPC application, but also deep learning application. And you can also think of workflows combining these. A lot of newer workflows are happening where you try to do deep learning for some part, followed by HPC, followed by deep learning. So all those things you can do very nicely using a single converged software stacks like MPI. And here I provided some of the details on the out-of-code training, hybrid parallelism, as well as commercial support. So we continue to work in this area, and we hope that some of these solutions will enable the DL community to achieve scalability and high performance for their distributed training. So I'd like to thank all our sponsors, and not only the sponsors, but more importantly, I'm very grateful of my all the work being done by the past student staff. What I'm trying to summarize here is like a 20 years of effort. So a lot of these people, if you take a look, they have graduated and working in all different places, national labs, industry, but as a group, we are continuing and building on their work. So every time I give a presentation, I want to provide credits to all. So with this, let me stop here. And if there are any quick questions, I'll be happy to answer. Or otherwise, you can always send me an email, and I can have also follow-up discussion. Thank you.
Thank you, Dr. Panda, for the wonderful presentation. We have one question from CINECA.
Sure.
Federico Ficarelli is asking about, is the RDMA transport for gRPC available in gRPC upstream? If not, is there a publicly accessible fork where it is available?
Yeah, so we had, I didn't indicate this here. If you go to this HiBD data, HiBD, let me try to, just go to the HiBD. We have an TensorFlow accelerated with gRPC and RDMA. We have a version, but that is a little bit old. So that students and all graduated, so we are not able to continue that project. But our MPI-based solutions actually delivers far better performance than the standard gRPC RDMA. So that's why we have moved to the MPI-driven solution.
Thank you, Mr. Panda. Thanks a lot. And if there are any more questions, people please do share it through the chat window. Mr. Panda will answer it later or after this presentation. Thank you very much, Mr. Panda. I appreciate your time and effort on this. Thank you. And audience, let's move on to the next presentation. We have our European AI leader, Florin Manila, who is going to share about the AI features on IBM Power System. And Florin, please go ahead and start your presentation.
Thank you, Ganeshan. Can you see the presentation?
Yes, Florin, go ahead, please.
Okay. All right, so I know that we are late, and I'll try to be more precise. I'll focus more on AI operation. So what that means for you when you're trying to run all these things on a cluster like this. One of the more important thing I want to mention here, I will not discuss about it, is that we see for this combined HPC and AI systems a mix, obviously between the workloads, between the traditional high performance computing, which is typical simulations, and machine learning and deep learning. And therefore, there is as well the need of at a certain point consume those models that we train them, and therefore to expose them via an API and something like this to be included into the simulation pipeline. I will not discuss about this, but I will just present from the software stack perspective what can be, what we do as IBM. Right, so one thing we see typically are the data sets, which are larger and still continues growing. Other ones are, as you can see here, the GPU memory capacity, 16, 32, 14, the latest generations. Then we see as well a lot of concern about the CO2e per training cycles, and therefore, what you can do to, lower down the number of trainings that you're going to run for your experiments, as well as, various neural networks which are out there, and therefore they are introducing a couple of challenges on a cluster like this. So first of all, whenever you want to scale, you have to consider the data that you have, how you can, move that data from a centralized storage close to your compute node, how you can pass that, how you can really, if you use images, how you can decode, let's say if you use JPEGs, the images, and can move them faster to the GPU. So those are some challenges. Neural networks, I think prior to my presentation, there were a lot of information about the scaling of those neural networks. And not all of them, they scale well. ResNet 50 is one of the best, which is, which is out there scaling very linearly. However, in general, the researchers, they build their own neural network architectures, or they chain, or they take two kind of network architectures and combine them, for example, ResNet 50 with VGG16. And therefore, those tends to be, billions of parameters. If we even look on very large, is the same approach. And therefore, always you need to understand your neural network architecture, and then the limits that you have on the system, on the frameworks, and when you scale that, what that means when you consume GPUs. Because if you have a network that doesn't scale well, but you requested 128 GPUs, and the utilization of a GPU will be roughly 60%, what's the reason to do that? Then we have the computational side, and therefore there we are mostly looking on the software stack, what's going on there, and speak in particular to, for example, how we scale. We use Spectrum MPI, NCCL from NVIDIA, MAVPIC, or any other kind of library when we try to do that, and obviously the math behind the stories. From the distributed deep learning, obviously we see those four directions, and there are some others, but those are the most utilized. So single accelerator, this is the default mode for majority of the models and frameworks. And then data parallelization and model parallelization are obviously always people, they try to combine these two, but we see more model parallelization. And then we have the data and model parallelization, which are a little bit more complex when you try to span this across multiple systems up to a certain extent. And as you go to more advanced things on high resolution images, you can, try to think that the data can represent a specific region in an image. And that can be then, that region can be, send it to one GPU, and then you have another region to another GPU, and so on and so forth. So there are more complex things going on. So large data sets, they present a challenge always. You have to understand how you can partition the data that you have, how you can load that into the system memory, what's the memory available for the data in your GPU versus the kernels which are running there, and how you can adapt to the batch size, and ultimate how you load this data into the GPUs from the storage, from the compute node, how many workers you dedicate, and so on and so forth. Those are affecting at scale the performance of your trainings. Right, so a couple of misperceptions. This is the AC922 internal architecture, and I highlighted here that, by default frameworks that you're going to use, a single GPU. So if you fire up Keras or, for example, TensorFlow, PyTorch, by default, the models that you're going to use there, they will use NVIDIA or a single GPU, so probably the GPU ID 0 in the beginning. And then if you want to go let's say, to utilization of more than one GPU in the same system, there are multiple ways to parallelize the network depending on what you want to achieve. But like I mentioned, the best approaches are the model and the data parallelization. And the first can help you with your model, if the model is too complex to fit in a single GPU, while later can help when you want to speed up the execution. The main idea is that you pass your model through the method, and then it's copied across the different GPUs. And then the original input is split into chunks, which are, let's say, fed to various GPUs, and then they are aggregated as a single output. And this method can be used for achieving parallel training and prediction, and obviously, nevertheless, can present the faster training times for your experiments. And another thing is to go and try to see, okay, you can have multiple systems, and then you can parallelize your model across multiple systems, and therefore this is a little bit more complex, because in this case we always tend to use the all-reduce or MPI all-reduce function, which it synchronizes data parallel distributed deep learning in a couple of steps. It computes the gradients of the loss function using the mini batches on each GPU. And by the way, those batches have to be adjusted based on the number of GPUs typically you want to use and the type of data that you have. Then it computes the mean of the gradients by inter-GPU communication. And at the end, finally, it's updating the model. And this is, batch by batch by batch by batch. But this is involving as well the RDMA communication, MPI communication, gRPC if you choose to use that over the TCP/IP, or RDMA if there's that implementation somewhere. And then you need to understand to have the topology, to be aware of the topology of your cluster and the nodes that you want to run, and so on and so forth. So there are many implications there. So for example, in the Keras, there are a couple of scenarios where the training models weights are merged on CPU, or you can merge them on the GPU. And we have here on the right side the use case that you have it with AC922, where you have the CPU linked to the GPU with NVLink. So a couple of things, like I mentioned, batch size. Batch size when you are trying to train, and let's say you have a model which is using a single node, and then you want to scale on multiple nodes. Many times we see that you need to decrease the batch size as you increase the number of GPUs. Then you have to save your parallel models, obviously. Counting the available GPUs has a nasty effect, obviously, and so on. This is something we see almost always. It's a snapshot. We call it GPU data starvation. When you just fire up some Jupyter notebooks, or you can have your batch Python script trained, which has to do something. We see that even if you occupy the whole GPU memory, which typically TensorFlow tends to do that by default for caching purposes, but the GPU utilization, it's 0. Right? Or you can see 0 and then it's 100 and still waiting for a couple of seconds, and then it's going to 90% and so on. And therefore, when you see these kind of things going on, you need to investigate, what's going on under the hood, why you don't load the data much faster, how many workers you have assigned for loading the data, what kind of libraries you're using, and so on and so forth. So you need to pay attention when you actually request compute nodes for your jobs. And then, I will advise to go and check the GPU utilization during the training and see what is the good, if they have a good utilization, which roughly I will mention here, above 85%. Right, so let me go here. As you want to, for example, let's say you take a code from a Git somewhere and you want to do, for example, the multi-GPU. In this case, we have Keras. You need to just add a single line here from Keras utils import multi-GPU model, and then your model will be able to scale across all the 4 GPUs or 2 GPUs, depending on how many you requested from the Slurm. Another thing is when you try to parallelize your model, and then in this case, you can even have refined things. Okay, I want to have 4 GPUs. I want to use a specific loss, in this case, the categorical cross entropy, as you can see here. And then you can indicate the number of epochs or batches, but those are typical things when you do it. But you have those parallel models calls that you need to bring into your Python script to make it work. Another thing I will advise here is when you work with large data sets, as you can see here, I added here when you save your models, your training steps at every epoch. Just because in this way you will avoid retraining from the beginning and then obviously consume resources on the system. And the same thing when you work with large data sets, I will advise to use binary formats. So TensorFlow records or HDF5 will help you achieving better performance and saving a lot of time in training. Another example here is to have the CPU relocation, the weights merge on the CPU, which is the case for other systems. For ACNI22, I will advise always to merge the CPUs into the GPUs, and that will be, the training will be much faster. Not much, but it will be much faster. Right, so from the software stack perspective, we're concentrating as IBM on what is highlighted here on the distributed computing, collecting machine learning and deep learning frameworks and libraries together, extending the capabilities to governance, AI, fairness, explainable AI as well, and try to understand how we can provide APIs to be consumed when you try to serve those models in the production for inference. So you should build any pipelines and so on. So you want to use them in your, for example, simulations, if you want to use to either do defeaturing or anything you may want to do. So we have the Watson Machine Learning Community Edition. We call it WMLCE, current at 1.7.0 as a version. So this is a collection, or like I mentioned, of the frameworks and libraries, including CUDA and NCCL cuDDN libraries. What we bring here is, we have TensorFlow, TensorRT, if you want to consume this for inference and optimize and do the pruning for your models. Then you have Bazel as well. So if you want to compile the latest TensorFlow from the Git, you can do that based on Bazel that we ship there. Rapids AI, QDF and QML are there. In terms of PyTorch, we have as well Apex version, which will help you with the mixed precision if you want to train a mixed precision. XGBoost, SnapML is an IBM implementation of the GLMs, majority of the GLMs which are out there, but using GPUs. And for example, if you use scikit-learn, you know that you don't have GPU acceleration with it. And we have majority of the implementation of the GLMs in the SnapML library that are accelerated by the GPUs. And there are 3 types of the implementation: the local, which you can use it on a single node. And then we have MPI and Spark, where you can really use it on the distributed training. Then there is Dask, which can help you, from my perspective, very much on loading massive data on your training processes. So it's saving a lot of time. In addition, we make it part of the WMLC of the Spectrum MPI, Horvath, and IBM Distributed Deep Learning Library. For let's say better transparency, you can export your models in open neural network exchange formats. So TensorFlow and PyTorch, Caffe, they support ONNX. And if you train and then you can give it to someone and say, okay, here is my model which I trained, you can give it in a ONNX format. As well, you can import if someone is given to you. Then we have the large model support, and I will speak a little bit about it. And then which is extending training of the models beyond the GPU memory into the host memory. And for fairness and bias detection, for example, we have AX360 and AF360. And all those packages are delivered via 3 major ways. One is via Conda channel, and I will show you how you can install this in just 4 lines. Another one is via the Docker. So on the Docker Hub, if you go and search for Power AI, you will see all the packages there and so on and so forth. And the third one is via Red Hat UBI images for those that they use as a workload manager, Kubernetes, or anything like based on Kubernetes like OpenShift and so on. So we can cover containerized environment and bare metal. And as I seen that you do support Singularity, you can import the WMLC containers into the Singularity with just Singularity import command. As I mentioned, we have a strategy for serving those things. So we have the TensorFlow serving server included into the WMLC. You just have to install it additional with the conda command, conda install. TensorRT as well is part of it, ONNX, which are part of the inference side. So the goal is to have the same kind of software stack that can be used on a training system at scale. It can be used on, let's say, an interactive system with Jupyter Hub or Jupyter Lab, or can be used for an inference server when you try to serve those models and expose some APIs like TensorFlow serving is doing, or Triton server is doing. And then we want to have then the same architecture, the same approach running on x86 as well, CPU or GPU accelerated, if you want to give to someone and they just get everything running in a couple of minutes on the bare metal system. If you go on the Conda cloud channels and you search for Power AI packages, you will see the AI 360, IFF 360. So if you have projects and you want to really, just try to understand and find the biases there, or try to remove the biases, this is a good way to start, and it's very simple to install. As you can see here, just the Conda install Power AI. From the channel Power AI IF360 or IX360, and it's just they are just on your user profile. Docker containers, so we have them on the Docker Hub from 1.5.2, and you have various versions. The same thing is happening on the Conda. Though on a cluster like Marconi 100, I will advise to use Python virtual environments. And you can move to a version or to another one based on the code that you have. So if you have an older code that, for example, you need TensorFlow 1.15, you can go to WMLC 1.6.2, install it, and then if you want to go to the latest version, you can go to another virtual environment, and so on and so forth. And everything will be dependent from all those versions in a virtual environment that you can activate when needed. From the installation perspective, you need to install on your user account. You need to download with Vuget or any tool that you like, the Anaconda from Anaconda website for PowerPC Little Endian architecture. After you install that, you need to add WMLC IBM contact channel. There is a command here. And then you create your Python environment, virtual environment. For references added here, WMLC 170. In general, which we advise customers to keep as a name the version, because it's much easier for them to remember after that. But you can put whatever name you want. And you can choose Python 3.6, 3.7 for the latest one, or if you have older codes, you have to go for older version of the WMLC. Then you activate your channel, your Python environment. There's one command, it's called install Power AI, which is like a metadata tag that will grab all the TensorFlow, PyTorch, related dependencies, CUDA, CUDDN, and so on and so forth on your /home Anaconda and Anaconda 3 and then environment name. And even if you want to add additional packages, for example, if you need CUDA development kit or additional compilers, you can still use conda install, for example, CUDA dev, and this will bring all on your profile and propagate this into your Python path, so you can then easily compile everything. So the admins of such cluster, they don't have to install the CUDA on the cluster on the compute node. They just need to be sure that the CUDA, the GPU drivers, the latest versions are there, and then you are up and running. So we decouple somehow the administration side from the user's perspective. Obviously, that means that they can create modules where they can package this. But from a user perspective, you are free to just install this, and you're up and running, and you're independent mode, and can install your own packages and so on. And you can even combine with pip. So the large model support, what we have done in the last 2 years and a half, this started, as far as I remember, in Japan, IBM Research Japan, is to try to swap up the tensors while you do the training. So we know that the GPU memory is not enough, always is not enough. So you always occupy the GPU memory with some kernels and so on, and there is little space then, typically left for the data. And if you work with models which are very complex, or if you work with data sets where you have, we're using high resolution images, for example, from satellites, typically what you do, you need to slice those images, or you need to resize the images to scale them and, and use a better batch size. So typical people, they use a batch size of 1 or higher resolution images. So what we have done, we find a way in TensorFlow, in PyTorch, and in Caffe to swap the tensors which are not used from the GPU memory to the host memory, because we have this NVLink between the GPU and the CPU. And we have more space for the data. And this is a continuous process, and it's very simple to be used. You can use it in the TensorFlow. Here you have it on the left, the lines that you need to bring. My personal implementation is the one in PyTorch, where you just add, torch CUDA set enable LMS, because by default is not enabled, and then this will use the large model support. And we have seen as well in some cases training reduction whenever we are keeping the same batch size. So that's very nice, and you should explore this if you have some opportunities and large, let's say, models or high resolution data that it needs a lot of memory into the GPUs. So what's possible? This is what we have done so far. So we have seen some interesting improvements in image resolution whenever we process. Or if you use 3D unit for in semantic segmentation, we have published a lot of information about brain scans and how the large model implementation in TensorFlow, we call it TFLMS, at version number 2 right now. It's actually helping people to train much faster and a higher resolution. Right, so distributed deep learning, I will not spend too much because it was already discussed, but in general, we are interested in a couple of things for data scientists into tools to automate the topology detection, creating of the rank files, automating the MPI run options, and obviously scaling in an efficient way. So always it's a trade-off between what the technology can give it to you, but how easy you can use a cluster like this, how easy you can train, how you can use your package, and how easy it is to find support, and how easy it is to you find the documentation. So I will just mention here what we provide in terms of distributed deep learning within WMLCE. As you can see here, we are packaging the Spectrum MPI from IBM. We have the NVIDIA and CCL, so you don't have to point in your Python pad the location of the Spectrum MPI from where the HPC guys are using. You don't have to do that. If you install the WMLCE, it's coming with everything there, so you don't have to do nothing. The same, we have a library, a DDL called a Distributed Learning Library coming from IBM Research that is as well supported by TensorFlow that you can use either as a backend for Horvath or as a standalone Python library. And in terms of integration, obviously we included Horvath, it's DDL there, and you have option as well, distributed strategies like gRPC within TensorFlow. How you can install by default, when you conda install Power AI, you don't get Horvath there. So you need to do an extra step by doing conda install Horvath. By default, I believe will come with Spectrum MPI backend, but you can compile it. There's just a single command where you can do it, and you can compile it with a nickel backend, for example, or DDL backend, so you can switch the what is recommended by IBM. Yeah, this is there. Just have to use it. Right. So you see here, it's just a DDL run. This is IBM tool to discover the topology, create the MPI ranking. We have as well the integration with our own scheduler LSF. So we read the hosts which have been assigned to you. For example, when you run across multiple systems, you always go to a workload manager and say, like Slurm, and say, or LSF, say, hey, give me so many GPUs for my training. But you don't know how many, you don't know the names of the system that will be assigned to you, and therefore you cannot indicate in the command line. So you have to read that. We were integrating these things with LSF. In addition, this is the Horvath architecture. It's all about ranking and all about each tower is assigned to every rank, local ranks, for example, or individual, which are attached to individual process. And therefore, it's very important to see and understand how many cores you have in the systems and how many GPUs have been assigned. So to assign a core to GPU ratio in a good way. You can run with MPI run, for example, any kind of Horvath related Python script, TensorFlow, PyTorch, and so on and so forth. With MPI run number of processes, and then you indicate the hosts. Or you can use Horvath run that will actually help you with all the topology as well. So if you're discovering that you have InfiniBand there, it will pick up for you by default, so you don't have to put all those things there, which are typically not so nice to make them. And then there are a couple of things you have to, when you do distributed deep learning, I would always advise to do things like saving checkpoints at every epoch. You don't know when your job will be killed by someone or something is going on. And if you spend so many days and hours, it's a pity to lose all your job. And I will finish with this. I added here some Slurm template, and I know that you have Slurm. So this is a template, a batch template, assuming this is for PyTorch, but it's similar for TensorFlow. So what you do here, there are just a couple of things, how many GPUs you want to request per node. In this case, or your case would be 4. How many nodes? So this is for 16 GPUs in total. An example. Then you should request in exclusive mode when you train those neural nets, because if someone else will execute something on that node, you will get code out of memory and you don't know from where that is coming. We have seen this in other environments. And then your profile here, you can put your home, then your Python environment, the name, and what is your conda root, so you can adjust this to your class that didn't have access to your system, but I believe it will be similar. This is from MIT Satori cluster, by the way. And then in order to read the nodes which will be assigned by Slurm to your training, you need to export the node list and through the Oak to grab that and then put that into Horvath run as learn a number of tasks and node list. This is a trick we have done to just use Horvath run, automate the ranks which are automatically based on the discovered topology and the number of nodes which are assigned. So this is just for you. It's a copy. If you just copy paste this, it should work on your environment. In terms of Horvath within PyTorch, there are a couple of things you need to add, well documented, or either on PyTorch, either on Horvath. There are a couple of examples. This is, for example, the MNIST PyTorch example, where you need to import the Horvath into PyTorch. You need to then initialize the Horvath library. And then add a couple of things like, for example, the number of threads there that you want to use, and so on and so forth. All these things. So it's not that simple. Like in the Keras with the multi-GPU, you need to add a lot of things, like including the optimizer, what optimizer you want to use. Like as you can see here, you need to pay attention to all these things in order to have a good distributed training across all your systems. Right, so any questions? I think I'm on time. Manishan, any questions? If there are, I'm happy to take them.
Florin, thanks for your detailed presentation on AI at scale using IBM Power Systems. Audience, any questions? Panelists?
I have one question.
Yeah, please go ahead.
Yeah, thanks. Thanks for the excellent presentation, Florin. This is Argo from UW Platteville. So I have a question regarding that IBM's LMS, that large memory support for machine learning. So, if let's say I have a huge amount of data, so of course, at some point of time, it is not, I cannot hold it on memory. So what type of technology is it using? Is it using some kind of NVLink technology? Or, when you are saying large data support, are you connecting to the DRAM, or are you optimizing the reading and writing from or to disk also?
All right, so what we do is just, so when you start, for example, let's take TensorFlow. When you start, for example, your training, right? You construct your graph. While, after you construct your graph, there is no way you can really, change that graph while, has been already constructed. So that will be sent to the GPUs, and then the training is starting. So what we are doing, we actually use the communication between the GPU and the CPU, which is NVLink 2.0, 150 gigabytes a second. And while you are training, we are swapping up some tensors from the GPU memory into the host memory, into the RAM, where we have 170 gigabytes per second per socket. That's the theoretical throughput. And we make more space for the data. And in this case, for example, if you are training, let's say for semantic segmentation using satellite images, what you'll do is, first of all, from a large image, you'll segment that image, and most probably you'll end up, if you have a high resolution, let's say 7 meters, you'll end up with a batch of 1. So you send 1 image to the GPU at the time to be processed. So what we can, because there is no space into the GPU memory for, let's say, another image. So in that particular case, when you enable large model support, during the training, we see tensors. So we're swapping into the system memory. We can make more space for the data, and you can increase the batch size, for example, to 2 or 3 images. This obviously is depending on the capacity of the memory you have on a compute node. So, for example, I believe in the cluster of Marconi, there are 256 gigabytes of memory per compute node, and therefore your limit will be of the large model support will be bound to the maximum limit of a compute node, which in this case probably will be around 220 gigabytes, assuming the rest will be for operating system and so on and so forth. And if you increase the batch size even more, you will, at a certain point, you will see that you don't have any more space. So what we use just the system DDR4 memory to swap the tensors there and take them back when needed.
Okay.
We don't go to the disk and so on. We have recommendations for some cases where we are dealing, for example, where people, for example, at Satori, where I have access, and I did architecture of, so Satori is the MIT only AI cluster there. And what we did there, we architected the solution with 1 terabyte of memory per compute node. So people, what they are doing when they were working with, let's say, 1 petabyte of data, they are chunking that, and they are storing into so if they are not enabling large model support, they create automatically on the fly a virtual disk on the compute node where they push the whole memory. In addition, I don't know here if at Marconi they use NVMe, local NVMe inside of every ACINE22, but when you have large data sets and you have NVMEs inside, PCIe NVMEs inside of ACINE22, and you have a spectrum scale, so GPFS in the back, there is local read-only cache option into the GPFS, and that can, LROC we call it, that can make those local NVMEs adapters as a read-only cache for the distributed file system. And what that means is that whenever you always tend to read the same images, because this is what you will do, right? You will tend to read the same images now epoch after epoch after epoch. This will cache into a 1.6 terabytes local NVMe, so you'll never go and read data from a storage. And if you have so many compute nodes like they are here, you will have a better performance in reading the data. So that will increase the GPU utilization. But those are for extreme, let's say, users where they use massive data sets.
Great, thanks for that.
Thank you. Yeah, thank you, Florin, for the detailed, answer also for the question. Thanks again. And, let's move on to the conclusion here. I'd like to thank the presenters, organizers, especially CINECA team for the workshop today. Thanks to panelists as well as the participants who actively participated as part of the workshop. And, I would like to invite Massimiliano to give a closing note for the workshop. Please go ahead.
First of all, thank you to Gans for his incredible amount of work to prepare this workshop, and thank to all presenters for very interesting presentation, and finally to the people that participate to the workshop. So thank you, and I hope to see you as a CINECA user in the future. Goodbye.
Thank you. Thank you to all. Thank you.